What's up? What's up, AP Chem? I'm so excited for y'all to be here tonight. This is the very Amanda Duemeril. I'm the founder and CEO of Fiveable. I was here for one of the previews, helping out the Chem crew, and I'll be around all night, just like in the chats, hanging with y'all. Just trying to keep the vibes good because it's time for Chem, and I don't know about you, but I'm excited. So let me hear you in the chat. Let me see a 1 through 5. How you feeling about your Chem test right now? So a 5 if you are like, honestly, give me the test right now. I got this. And a 1 if you're like, I'm gonna need some more time. And we'll kind of see how we're doing. So we've got a whole bunch of you here right now live. This is gonna be a fun night. So we're gonna go through units 1 through 5. It's a lot of content. It's a 3-hour event. So I want to give you a quick little rundown of what you are seeing in Crowdcast and how it works so that you know what to expect. So the chat is like a big group chat. This is a place for you to, ask questions or chat about things, but there are a lot of you, so sometimes the chat goes kind of fast. So we just want to keep the chat just like on topic for the most part. And then on the question tab, the Q&A tab on the side, that's where you should ask your questions. So we have a couple of other students who are going to just be focusing on answering your questions there. So make sure that you put your question in the question tab. The other thing I wanted to call your attention to is this big old green button right below me that says AP Chem Cram Hub. What we've done there is we've linked the slides for all 5 nights. We've also linked this epic review packet that this team has made for you. They've basically taken notes already on all of the cram nights. So while you're watching, you can make a copy of that. You can highlight notes, mark it up, however you want to keep track of things. That's going to be pretty fun. So those are all the things that I had for you. I'm super stoked to have you here. As we've said before, our goal is for you to feel really confident for the test. Obviously we are rooting for you to pass, to do well. We're called Fiveable for a reason, but mostly because we want you to feel like every test is Fiveable. Like I could do that. I could get this score that I want. But at the end of the day, your goal is to just do it. Like you're here, you're doing the thing, and so your score is not going to make or break you. So that's all I've got for tonight. I'm going to give you probably several more pep talks over the course of these 5 nights. Like I've said, this is 3 hours, so we'll try to take a couple of like little brain breaks throughout. Definitely make sure that you've got water, stay hydrated, dinner, whatever you need. There is about a 10-second lag, and then if you are having any kind of other issues, just refresh your screen. All right, with that, I would like to welcome up the Chem team. They're going to introduce themselves, and we're going to get started. Let's go.
All right, what's up, guys? My name is Jahangir. I'm going to be teaching Unit 1 and 2 tonight. And for Night 2, I'm going to be teaching Unit 7. And I'm from Texas. So if you guys are from Texas, let me know in the chat. And I'm taking the AP Chem exam just like you guys. So I'm in the journey with you. And I'm going to be teaching you, going through the content. So it's going to be a fun time.
Howdy, folks. My name is Elias. I'm going to be your Units 3 and 4 expert. Little tidbits about me. I'm personally from Ohio. I took the AP Chem exam last year. And to get to know me a little bit as an individual, my favorite movie is the absolute hit Abraham Lincoln Vampire Hunter. I'm so excited to be able to teach you guys tonight. And I hope you guys have a good time in the process.
Hey guys, I'm Anuba Yanzan. I'm a senior at the Academy for Allied Health Sciences. If anyone knows where that is, it's in New Jersey. So any people from Jersey, definitely say it in the chat because go Jersey. Again, I'm also taking AP Chem this year with Jahangir, not in the same class, but we're basically in it together and we're in it with all of you guys. I'm going to be your Unit 5 specialist. So hype for Kinetics because personally biased favorite unit. But yeah, so if you guys have any questions, we're here to help you guys out and we're here to like get a 5 and be confident for this test.
All right, let's get started. So, night one, we're going to be reviewing units 1 and 2 for AP Chemistry. And just a little follow-up, follow us on Think Fireball on social, on our TikTok, Instagram, YouTube, and LinkedIn. And here's our cram schedule, like we said, for night one, which is April 26th. Today, it's units 1 through 5. Night 2 is going to be April 27th, which is units 6 and 7th. 6 and 9, sorry. And unit 3 is going to be MCQs, where we're going to break down some MCQs, have some tricks for you guys to know. And night 4 will be FRQs. So that's going to be where we're going to have some tricks, some pre-recorded videos, so that you guys can follow along. And night 5 is going to be our final grand finale, tying everything together. So let's look at unit 1. And unit 1 is atomic structure and properties. So this is 7 to 9% of exam. And this is pretty simple. If you took chemistry in your sophomore year, this is basically the chemistry that you learned. And we start by moles and molar mass. Now, let's start by talking about atoms. And there's some atomic particles, and we have protons, neutrons, and electrons. And if you guys know, protons are positive, neutrons are neutral, electrons are negative. Protons and neutrons are in the middle of the atom, while electrons are outside. And they usually have their mass is usually 1 for neutrons and protons, and electrons is a lot smaller than that. And moles are found by getting the grams of the substance that you're calculating over your molar mass. And you can always find your molar mass on the periodic table right here. And you're going to be given the periodic table, not this one, not this cool, colorful one that looks really awesome, but you're always going to be given a periodic table on the AP Chem exam, and it's going to give you the molar mass, which is the amount of grams per mole of an element. It's going to be under the element, the sign, its name, like hydrogen, it's H, so it's going to be that number under. And for hydrogen, if we go through that example, we have 2 moles of hydrogen, and if we multiply that by 0.008 grams per mole, which is the molar mass, we get the grams that are given. So we can switch it up, and our formula is just moles over molar mass, or the grams that were given over molar mass gets us moles. So let's look at the famous number, Avogadro's number. And Avogadro's number is 6.022 times 10 to the 23rd power of atoms per mole. Or you could also think of it as 6.0223, because at the end there is some number that can be rounded, but that's your Avogadro's number. And this number helps us convert from atoms to moles per gram and vice versa. And there's the dimensional analysis, which is a method for converting from one unit to another. And if you don't remember this step, try ordering the conversions so the units cancel out. So let's look at this problem real quick. We have 50 grams of carbon dioxide, and we multiply that by 1 mole of carbon dioxide, and then we have 44.01 grams of carbon dioxide, or molar mass, and the grams cancel out. Now, I believe this system is called the Punnett setting up your picket fence. That's what we call them in chemistry, at least in my chemistry class. That's what we call them, where you try to take out the units, so then you get your moles, and your numerator power is going to be the units you get. So then you multiply that by your moles of carbon dioxide to the atoms, that Avogadro's number. You cancel out the moles, so you get the atoms of carbon dioxide. And if you wanted to get specifically the oxygen, then you have to set up the mole ratio. And the mole ratio is a ratio of the moles. As you can see, there are 2 atoms of oxygens for every carbon dioxide. So you just multiply your 6.84 times 10 to the 23rd power of atoms of carbon dioxide, and you get 1.37 times 10 to the 24th power of oxygen. Now we look at mass spectroscopy. And mass spectroscopy is a technique used to find elements using mass of the relative abundance of isotopes in the sample. So you're basically given different isotopes, and you're trying to find the weighted average and comparing them to the periodic table. So you're usually given a graph, and you look at those peaks, and whatever you find, multiplying the percentage by your mass on the bottom, so the intensity percentage over your isotopic mass, you multiply all of those and add them up, you get your molar mass. And if you look back into your periodic table, you'll see that it is magnesium for this question on my, I believe, Hopefully it's my right. But isotopes, since hopefully you guys understand what isotopes are, but they're just naturally occurring variations with different numbers of neutrons. So it's like a specific element, but it has different variations of it. And there's also the average atomic mass, which is the weighted average of all natural occurring isotopes within the element. So for example, carbon has two natural occurring isotopes. There is carbon-13 and carbon-12. And the only way for us to have different variations, different isotopes, is having a different amount of neutrons, like the definition states. So there's going to be a 1.1% of carbon-13, and for carbon-12, there's going to be 98.9%. So we multiply the percentage by our isotope, and we add those up in order to get our average atomic mass. Now let's talk about elemental composition of pure substances. Now, definition of this is that you need to be familiar with the three states of matter. And a pure substance is a single type of atom or molecule with no variance among the samples. So this could be made up of a single atom, like a bar of pure gold, or compounds made of atoms with two or more elements bonded together, such as water or salt. And there's a law of definite proportions, which basically states that any pure component will always contain the same ratio of elements. Now, example would be water will have 200 grams of hydrogen and 100 grams of oxygen, and the elemental composition ratio remains the same. See, in water, we know it's H2O. So we have that doubling effect. See, we have oxygen, which is 100 grams, but then we have 200 for hydrogen, because we have to account that in oxygen, we have two hydrogen, one in water, sorry, we have two hydrogen, one oxygen. So it's a double ratio, that mole ratio. And for the applications, we have formula units, which is a lowest whole ratio of describing an atom. And like we said, water has a 1:2 ratio of oxygen to water. And one of the formulas that you have to be familiar with, and it's going to be on the FRQs or even the MCQs, is the empirical formula. Now, there's a specific way of solving the empirical formula, and we'll go through that through our MCQ practices and our FRQ practices, and maybe even the quizzes today. But in night 3 and nights 4, we're also going to have more quizzes geared towards empirical formula. But this is just a simplest whole ratio of atoms in the compound. So basically, the glucose, which is C6H12O6, can be reduced to CH2 and O. It's just the smallest amount of ratio that we can reduce that to, and that's the empirical formula. Now let's look at atom structure and electron configuration. And there's a John Dalton atomic theory, which states that each element is made of invisible and indestructible atoms. All atoms are given an element that carry the same properties. Atoms combine in whole number ratios to form compounds. And finally, a chemical reaction changes the way atoms are bonded together. Now, in Unit 4, which Elias will talk about, the chemical reactions can break down intramolecular forces, and we'll talk about that later, but that's just a thing to know. And next thing we want to talk about is Coulomb's law. And Coulomb's law is one of the laws you really have to be familiar with. And this is just showing how the distance between two atoms, or how the charges between two atoms, can affect this attraction. So for example, if we have a farther distance between our atoms, there's not going to be a lot of attraction. Think of it like a date, right? If you're not close to the person that you're attracted to, you're not going to have that attraction. You're not going to have a good first date. And with that distance, we need to be closer. We need to be closer with each other so we can have that attraction. And same as the charge. If we have a higher charge, for example, calcium has a 2+ charge. And if calcium wants to bind to, let's say, sulfur, that's going to be a closer attraction, because calcium has a 2+ charge, sulfur has a 2- charge. So the charges are going to pull them together, and that's compared to sodium and chlorine, which only have a +1 charge of sodium and a -1 charge of chlorine. So you see the equation on the Coulomb's law, but if distance is reduced, attraction increases, and if charges are increased, the attraction between the atoms increase. Oh, and one thing to note, this is also important for atomic radius, because that's part of distance. If we have a high atomic radius, we're not going to have a lot of distance. We're not going to have a lot of attraction. But if we have a smaller a smaller atomic radius, we're going to have more attraction because we have less distance between those two atoms. Now, let's look at the Bohr structure, and Bohr says that electrons exist in energy levels, and this causes the energy of each orbital to be quantized. So the outer ring, the most outer orbital, is always going to contain valence electrons, and this is the s and p orbitals, which we'll discuss in electron configuration, which is the next thing we'll talk about. And there's core electrons, the inner electrons that are within the atom. It's the inner electron, and these include the d and f orbitals. Now, there's also many principles, such as the Alpha principle. Hopefully I pronounced that correctly. But you must fill the orbitals in order of increasing sub energy. So there's 1s1, 1s2, 2s2. You need to fill those electrons up, because I believe it's the two layers of the electron where you fill up 2 electrons, and when you keep on going, you're going to have 8. So you're going to have to fill up those 8, and that's for the Bohr's model of the electrons. And there's also the Pauli exclusion principle, which states in a pair of electrons they must be spinning in opposite ways, but you don't really have to know that. There's Hund's rule, which says that unpaired electrons must fill an unoccupied orbital before pairing with a single from another orbital. So just to bring this in layman's terms, it's basically stating that fluorine, it has I believe it has just 1 electron that's needed to be filled, and usually some elements like sodium will fill in that space. So that's how they make an attraction. That's how sodium and fluorine make that attraction, because fluorine wants an electron and sodium wants to give that electron, and it fills up that space that the fluorine has. And to find valence electrons, you always look at the outer shell, like we discussed. So now let's talk about electron configuration, and there's a boron electron configuration, which is 1s2, 2s2, and then there's p orbitals, etc. And the subscripts are the number of electrons. And boron, for example, has 5 electrons. And when you're setting up your electron configuration, you always want to follow the 1s2. You always want to start with 1s2. So for our periodic table, we go 1s1, which goes hydrogen, 1s2, and then over here to our lithium and beryllium, that's 2s2. And then we go into the 2p orbitals. And the p orbitals can fill up 6 electrons. So then we go all the way to p. Then we go to 3s2, or to 3s, and then 3p. And then we go 4s. And then I believe we go to 3d, which includes all of these over here. And I believe 3d can contain about 10 electrons. So that's pretty much the electron configuration. And there's also noble gas configuration, which allows you to state the electron configuration using a shortcut. So for example, we have helium, and helium fills at 1s2, or I believe this is helium. So it fills up the 1s2, 2s2, and then that 2p1. Oh no, this is boron. Sorry. The graph over here is boron, since we have 5 electrons. So it fills up that 1s2, 2s2, and then if it has that 1 extra electron, which is our valence electron, making it boron. Now let's look at photoelectron spectroscopy. And the definition of this is that a photon is just a light particle, and the frequency is waves that pass through a point in space in 1 second with light with higher energy that has higher frequency. And the photoelectron effect is when a proton hits a metal surface, it can emit an electron if its frequency is high enough. But for the AP exam, you really don't have to know the specifics of the photoelectrospectroscopy. All you have to really be familiar with is the graph. So here's a graph example. Now we have the number of electrons to our, I believe that's the y-axis, and to our x-axis, we have specific peaks of the orbitals. And when we look at the orbital arrangement, we're basically looking at the electrons. So you always want to start with 1s1, and as you can see on the bottom, that is ionization energy. So the farther we are, the higher ionization energy we have, the more likely that's going to be more our inner electrons. So as you can see for carbon, we have that 1s2 that's already filled up. Then we have our 2s2, and I believe we have our 2 2p2. So as you can see, we're filling up those electrons, and photoelectron spectroscopy just shows you how you can find the electron configuration. Now let's look at periodic trends, and this is very important to know. As you can see from the image, this is just perfectly illustrates all the trends that you need to know. And from a horizontal side of view, when we're moving to the left side of the periodic table, we are increasing the atomic number, and this is the same number of occupied electron shells. And from vertically, we are increasing the occupied electron shells by 1, and every element in the group has a same number of valence electrons. So as you can see, for our alkaline metals, we have a +1 for all of them, and then for alkaline earth metals, we have +2 charge. So they're basically the same charge going vertical, and from horizontal, we have an increased atomic number. Now, when we're going horizontally, we also have an increase in electronegativity. And electronegativity basically is basically the ability of an atom to just pull away another atom. So it's basically creating an attraction, such as oxygen. And in water, oxygen is the most electronegative compared to hydrogen. So it's going to pull the hydrogen towards itself. And that creates a strong bond. And that's a hydrogen bond, for example, which we'll talk about in our unit in night 1 tonight, unit 3. So, and next we have ionization energy increases from going from left to right. And the reason why ionization energy increases is because we have a higher amount of charge. We have higher amount of protons, and it's going to be harder because ionization energy is the energy it takes to pull those electrons out. So it's going to be harder to pull those electrons out when we have a higher charge, and when we're like oxygen, when we're having a stable and we're electronegative. So we're basically tight, and the protons are pulling the electrons together. So it's going to be pretty stable. It's going to be hard to take those electrons out. Now, atomic size increases going from right to left, or decreases going from left to right. The reason why atomic size decreases is because of those protons. And the protons, like I said, will pull the electrons together, pull the electrons more inward, so that we have a smaller atomic radius. Now, on the left-hand side of the graph, we're looking at ionization energy increasing going from down to up. And the reason why ionization energy increases from here is because when we're going down from the periodic table, like for example, when we're going down all the way from lithium or hydrogen all the way down to francium, we're increasing the amount of orbitals we're having. So there would be a bunch of orbitals in francium, and there's not enough protons to pull those together. So there's going to be a bunch of orbitals, bunch of electrons with it. So it's easy to pull those electrons out because the inner protons cannot pull it together. It's basically, I think of this as a security guard. Like protons are kind of like the security guard, and electrons are who they're protecting. And if there's just a bunch of electrons, it's going to be harder for our security guards to take care or to keep our electrons safe. And with the ionization energy, it'll just be easy to take those electrons away. Now, electronegativity increases when we're going from bottom to up, and pretty much the same thing. It's because we're having an increase in atomic size. And like I said, an increase in atomic size is seen going from down to up because there's so many orbitals. Like in francium, I bet there's a bunch of orbitals. So it's going to be hard for the protons to pull those electrons together, and it's going to create a bigger atomic radius. So there's also the effective nuclear charge, which we've been talking about, from going from left to right. And that's basically the charges, which is the actual amount of positive charge experienced in an atom. And this is just the effective nuclear charges found by protons minus the shielding constant. And this is known as the core electrons. So for example, for sodium, there are 11 total electrons and 10 are core electrons. Therefore, the nuclear charge is 1 because we have a valence electron. So you could think of the effective nuclear charge as the outside valence electron, especially for alkaline metals and alkaline earth metals. And I mean, we pretty much went over this. I kept talking about it. So we talked about electronegativity, ionization energy. There's also electron affinity, which when we go across the periodic table, we get more negative in electron affinity. But when we go down the periodic table, we're becoming more positive in that electron affinity. And the ionic radius is different from the atomic radius in that it's with metals. And metals tend to lose an electron, become cations, causing the radius to decrease significantly. And nonmetals gain an electron, making them larger. So that's pretty much the difference between atomic radius and ionic radius, because ionic radius usually includes metals and atomic radius most of the times doesn't. But if we look at atomic radius, like we talked about, going across, our atomic radius gets smaller because the atomic radii get smaller. So because we're increasing nuclear charge, and it's going down a group, we increase the atomic charge because of the orbitals. And that should conclude the periodic trends, because we did talk about them in the other slide. And let's move on. We have unit 1.8, which is valence electrons and ionic compounds. And they're types of elements that you need to know and their characteristics, such as metals are good conductors, they're shiny, malleable, and they're ductile, and they're left in the they're left to the staircase. And the metalloids are properties of both metals and non-metals, and these are the only 7, which is the staircase you can see, the orange colored. And the non-metals are bad conductors, they're brittle, and they're pretty much on the right side. They include carbon, nitrogen, oxygen, etc. Now, there are also different bonds, and we'll talk about those bonds more in Unit 3, but there's ionic bonds which transfer electrons usually from metals to nonmetals. So it's just a transfer of electrons that creates a bond. And there's cations and anions. Now, remember cations, you can think of a cat, and cats are positive. Get it? So they have a positive charge, and that's what cations are. And they get that positive charge from, I believe it's giving an electron. And for anions, they get a negative charge from taking an electron. So you could think of it as if you're giving a gift to someone, you're spreading positivity and you're giving them a better day. And if you take something away, you could think of it like stealing, then that's a bad thing to do. So anions, they're negative because they steal electrons. Cations are positive because they give away electrons. And there's also the octet rule, which atoms need 8 electrons in the valence shell to be stable. And an example of this is table salt, or NaCl. And there's also covalent bonds, which is sharing electrons between 2 atoms, and these are for non-metal elements. And there are polar covalent bonds, which are usually unequal sharing electrons due to different electronegativities of the non-metals. And if you remember, being polar means that you have a asymmetrical shape, and you have lone pairs that bend the electrons, such as water. And there's also nonpolar covalent bonds, such as methane, the CH4. And these electrons are equally shared, and usually 2 atoms within the similar electronegativities. And for methane, we have the carbon, and then there's hydrogen, 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 hydrogen. And it's nonpolar because it's symmetrical. There's no lone pairs, and that's what makes it nonpolar. And the atom with the greatest electronegativity will have a partial positive charge. And in ionic bonds, the difference is so great that the electrons are almost stolen. Like we said, because anions steal, that's why they're negative. Now let's move on to Unit 2, which is molecular and ionic compound structures and properties. And this is also 7 to 9% of the exam. Now, we first want to look at types of chemical bonds. And we were talking about this before, but let's look at the Coulomb's law and its application to ionic bonds. And this helps measure the attractiveness between 2 atoms. And as you go down the group, the distance between the valence electrons and the nucleus increases, decreasing the attractive force and electronegativity. Now, if you're ever asked about a higher melting point, the high ion charge with the most energy is needed to break the bond. And you could also think of it in the context of covalent bonds. Now, if you're looking at a sort of molecule and it says that it has a higher boiling point, most likely it's going to have a higher boiling point because it can make some intermolecular forces that we'll talk about in Unit 3, but also because ionic bonds are one of the most powerful, one of the most stronger attractions, and covalent bonds are pretty strong. And for water, it has a higher boiling point because we have a covalent bond between our oxygen and our hydrogen. And for boiling water, we also create hydrogen bonds between each of our atoms. So that's what creates attractiveness between the oxygen and hydrogen. Oxygen and hydrogen, it's covalent bonds, but with different water molecules, it's hydrogen bonds. And for ions, there's a crystal lattice, which are ions ranged in three-dimensional patterns held together by a strong electrostatic force, and they're pretty good conductors, like table salt or sodium that has a crystalline lattice. Now, determining which bond will form. So for ionic bonds, the electronegativity difference must be greater than 1.7. There are questions that talk about these numbers, so you need to know that the electronegativity difference for an ionic bond, it must be greater than 1.7, and these include nonmetal and metal, and cations and anions are bonded. And for covalent bonds, the polar covalent bonds has a 0.4 to 1.7 difference, and nonpolar has 0 to 0.4 difference. And ionic compounds conduct electricity and heat when dissolved in water, and ionic solids have a high melting point, and covalent compounds have a low melting point and do not conduct electricity. Now let's talk about intermolecular forces and potential energy. And we have to differentiate, or intramolecular forces, excuse me. Intramolecular forces are the forces between two atoms in a molecule. So, for example, if we're looking at water again, H2O, the intramolecular force is covalent bonds, but the intermolecular force, the forces between different waters, are hydrogen bonds. And potential energy is just the energy that is stored usually in bonds. And for the bond length, it's the equilibrium bond length, that is the distance between the atoms that holds the least potential energy or the most stable. And bond energy is the difference in potential energy between separate atoms at the most stable phase. Now, bond strength is basically bonds with higher energies that are stronger and more stable, and vice versa. And bond order is the more bonds, the stronger the bond. So double and triple bonds are harder to break than single bonds. And go figure, because we have a bunch of bonds there. And for example, I believe it's C2 or carbon dioxide. It has a double bond between the carbon and the oxygen. So it's going to be harder to break that double bond compared to the bond between oxygen and hydrogen. So one of the graphs that we're showing right here is the repulsion from having potential energy, and there's some overlap in the attraction. There's a dip that you need to be familiar with, and when it comes back up to 0, there's no overlap, so there's no attraction. And you might be asked to compare one bond to another whose graph is given, so it's important to understand periodic trends. And there are specific graphs showing how a double bond differs from a single bond in terms of the repulsion and the dip in the potential energy, and that goes the same for the triple bonds. Now let's look at the structure of ionic solids, and we talked about that crystalline lattice. And the crystalline lattice is hard, brittle solids with a high melting point. Now, these structures of the ionic solids, these maximize attractive forces while minimizing repulsion. And ions fit well together and impacts force. And Coulomb's law, the electrostatic force between the cation and the anion increases with the charge and decreases with the distance. Now, remember, ionic solids cannot conduct electricity because they are fixed in their own position. It's only metallic solids that can conduct electricity, or they're the best in conducting electricity. And the last energy is energy released when ions form a solid. And usually when you look at a crystalline lattice, you'll easily identify, knowing that one of the elements, such as chlorine, and comparing it to sodium, one of them will be bigger than the other. Now let's look at this question. Does MgO or sodium and fluorine, do NAF have a higher lattice energy? And to answer this question, magnesium and oxygen have a 2 plus and a 2 minus charge, while sodium and fluorine have a 1 minus and 1 plus charge. So MgO has a higher lattice energy. And we talked about this before. I believe I had an example similar to this. I stated with calcium and sulfur, but with a charge based on Coulomb's law, we have a higher charge. So we're going to have more attractiveness compared to the charge of just sodium and fluorine, which are just 1. Now let's talk about Lewis diagrams. And Lewis diagrams are the most fundamental diagram that you're going to be asked to draw. And in physics, it's kind of like how we used to draw the forces. If you ever took physics 1, you had to draw the forces, like now I believe it was natural force, then gravity, and you could have forces on the other side or this side. But it's kind of like that, where you're drawing, and this is the most you will draw in chemistry, which are the Lewis diagrams. And there are some exceptions to the octet rule, and we talked about the octet rule is filling those valence electrons. Usually it's 8, so you want to fill those up. And the elements that can go out of exception for the octet rule include helium, I believe the next one is beryllium, and boron. And if the atomic number is greater than 14, you can add electrons to the essential atom to break the octet rule. So for example, there's phosphorus and chlorine 5 and sulfur fluorine 6. Now, some compounds have a double and triple bond, and atoms with odd number of valence. There's also atoms with an odd number of valence electrons. Now let's look at the Lewis structure of xenon and fluorine 2. Now, when we're drawing the Lewis structure, we want to draw it first, obviously, and the element that is the least in number, which is xenon, we're going to put that in the middle while we have fluorine on the outside. And if you're drawing water, for example, H2O, you want to put the oxygen in the middle and the hydrogens out. Now, usually you want to follow the rule that the most electronegative is going to be in the middle, but xenon is not electronegative at all. So you're just going to put that one in the middle because there's only one xenon. And to find each atom for the valence electrons, you add 8 plus 7 plus 7, because xenon we have 8 valence electrons. Fluorine we have 7, so that's going to equal 22. And we obviously, like we talked about, our central atom is xenon. So we want to draw the fluorine atoms and connect them to the xenon with a single bond and draw the valence electrons for fluorine, which we have 1, 2, 3, 4, 5, 6, 7. And when you have a bond between the xenon and the fluorine, we have one electron over here and one electron over here, and that's what creates a bond, those 2 electrons. And we add the remaining electrons around the central atom. And since xenon's atomic radius is greater than 14, we show that through the graph. And as you can see, for xenon, we have 1, 2, 3, 4, 5, 6, 7, 8. So it has those 8 electrons, filling the octet rule. Fluorine also has its electrons, and it also suffices the octet rule, because when you're calculating the octet rule, you're always looking at the bonds and you count those as 2. So as you can see, fluorine, we have 3 lone pairs, so 3 times 2, that's 6. And then for the bond, we include both of those electrons to fill the octet rule, and that would be the same for xenon and for the other fluorine to our right. And one tip is to not forget to add charges when drawing the ionic structures, and you want to account for the triple and your double bonds. Now let's look at resonance and formal charges. Now, resonance, or the resonance structure, can be drawn out in more than one way. And the only way we will get a resonance structure, or we have to create different structures of the same molecule or the same compound, is because we have either a single bond or a triple bond or even 2, but we have like some sort of bond that's different from others, and we can just switch them around. That's all creating the resonance structure is, just moving the double bond or triple bond, whatever bond you have that's peculiar or different from the other bonds, and you can just move them around. And the resonance tells us that in reality, the structure is an average of the possible Lewis structures. So for example, NO3 with a -1 charge, the bond order is the number of lines over the number of spaces, which is 4 over 3. And for the formal charges, these are charges assigned to the atom in a molecule. So to find our formal charge, we have to get our valence electrons minus our non-bonding electrons and our bonds. And the sum of the formal charges should equal the ion charge. And the most electronegative atom should have a negative formal charge, or the central atom should have a charge of 0. And this is the way the atom is in the most stable form. So as you can see on the picture to my right over here, this way, we can see that we have PO4, and on the other side we also have PO4 again, and we have that double bond, and we want to count the formal charges, and then that's where you get the overall charge of, I believe that's -3. Now let's look at the VSEPR, the valence shell electron pair repulsion and bond hybridization. Now you're really going to have to memorize your VSEPR graph because it's going to come very handy in the AP exam. And they're different families, and finding the steric number, which we'll talk about later. But let's look at the general formula for a linear form, for a linear shape. So this is, we have mx2, and this is a linear shape. So we have a 180 degree, and we have no lone pairs. You can see that on our central atom, we have no lone pairs. So it's going to be straight, and there's no electrons to bend our structure. And these include carbon dioxide and beryllium hydrogen 2, and there is a hybridization of sp. Now, to identify your hybridizations, it's pretty simple. So when you're looking at the bonds, for example, if the question asks you, what's the hybridization of M? And M is a made-up element, it's not real. But if it asks, what's the hybridization of N? We could just look at the bond, and that's our sp right there. We have one bond, and if we have one bond, we have an sp hybridization. Now, if we look on the bottom, we have the mx3. So we have one M and three X's, and these include CH2O, and we have BH3, and this is a trigonal planar shape. So it's going to it's going to kind of look like a triangle, but there's four elements, and it's going to have a 120-degree angle, and there's not going to be any lone pairs. And this is going to be an sp2 hybridization, because if it asked us what's the hybridization of M, we have 1, 2, 3. And if you have those three bonds, it's going to be sp2. Now, if we look on the bottom, we have mx2, and we have a lone pair. And this is our bent structure. And a perfect example of this is, I believe, oh wait, no, not water. Water has two lone pairs. But as we can see, we have NO2 with a -1 charge, and we have one lone pair. And the reason why it's called bent is because those electrons, those lone pairs, they kind of bend, they kind of move the X to the bottom. And that's what creates that curved shape. Now let's look at the next shape, which is our tetrahedral shape. And this is the MX form. And this is a perfect example of this is methane, in which our bond angle, which will be 109.5. And there's no lone pairs on this one either. Now, if we go on the bottom, we have a lone pair, and we have four elements, but we have one lone pair. And this is the trigonal pyramidal shape. And our examples are NH3 and PCl3. And when we look at the bottom as well, we have our next shape, which is a bent shape, but we have three elements, and we have two lone pairs. And a perfect example of this is H2O, because this is the one that I was talking about. We have two lone pairs, and those lone pairs bend the hydrogens. If we're talking about H2O, the oxygen will have two lone pairs, and it will bend the hydrogen, moving them a little bit closer to each other. And if we were asked what the hybridization was of either of these, and it said, what's the hybridization of M? We could look at M, and we have 1, 2, 3, 4 bonds. And since we have 4 bonds, it's going to be sp3 structure, sp3 hybridization. And over here, we have 3 bonds, but we have one lone pair. And that one lone pair still contributes to the hybridization. So that still contributes to sp3. So if you have a number of 4, your sp3, your hybridization sp3. If you have a number of 3, your hybridization sp2. And if you have a hybridization of 2, your hybridization is sp. Now, there's also other parts of the VSEPR formula or the VSEPR graph, and you really don't have to know these. You're not going to be tested on these, but it's still good to know. You have your trigonal bipyramidal, which has a 90 degree, and then 120, and then 180 degree. An example of this is PF5. We have the seesaw, which, and all of these are including, I believe, 1, 2, 3, 4, 5, 6 elements, or usually 6 elements, and then we have 5 elements, then 3 elements, and then 2 elements. So when our lone pairs increase, we can pretend that our lone pairs are adding to that number. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So all of them are going to have either elements or pairs that are going to add up to 5. And we can see our T-shaped structure, our T-shaped molecule, which has 2 lone pairs, 3 elements, Then our linear has 3 lone pairs, 2 elements. And I'm not going to bore you with the next part of the VSEPR formula. So that's all for, I believe that's all for Unit 2. Oh, we still have, I forgot, sigma and pi bonds. Now, sigma bonds are covalent bonds where the electrons are shared internuclearly, and pi bonds are formed by the unhybridization orbitals and perpendicular to the internuclear axis. Now, you could forget the mumbo jumbo that I said, and you can just remember that if we have a single bond, we have 1 sigma bond. If we have a double bond, we have a sigma bond and a pi bond. If we have a triple bond, we have a sigma and 2 pi bonds. And more pi bonds, the higher bond energy, and the shorter the length. So you can just remember this. If we increase the bond to 2, then we have 1 pi bond. 3, we have 2 pi bonds, and the sigma bonds all stay the same. We're always going to have 1 sigma bond for every bond. Doesn't matter if it's a double bond, triple bond. So we've been talking about hybridization, and this is just the atom orbitals that combine for a new hybridized orbital, and this affects the molecular geometry and the bonding properties. And there's sp3, sp2, and sp, which are the main ones that are going to be tested. Any electron orbitals are fused to go to lower energy states. So as you can see from the graph, we have carbon, which is 1s2, 2s2, 2p2. And as you can see, we're hybridizing the orbitals. So then we can have, because we have an s, we have 2s, and then we have 2p. So basically putting those together, so then we can have a straight orbital, straight electron orbital that is in a lower energy. And that's all for Unit 2. Hopefully you guys learned something from Unit 2, and I'm going to pass it over to Elias now.
Hey guys, so actually we noticed that you guys were wanting to do a little bit more hands-on, so I was wondering if any of my other co-hosts wanted to come down and help me with a little bit of surprise. We're actually going to take a pause to do a little bit of a quiz over Units 1 and 2. So I'm going to send that link to the presenter where it can be seen. Here, Anuva, I'm going to put you stage left with me. So yeah, we're going to take a moment. Once that once that quiz gets brought up, we're going to actually play a quick game real quick. Can I? Okay, yeah. So we're going to get that up in a second. In the meantime, is there anything that we could answer real quick? This is going to get pulled up in just a second. Oh, okay. Oh gosh. Okay, cool. We're good. We're good. That the format changed. I apologize. So anyways, so if you guys want to do a quick quiz in order to, do a little bit more hands-on stuff, have a little bit of fun while we take a break real quick, go ahead. You can either use the QR code if you're using a mobile device, or as I personally prefer, that link right there will also take you to the same exact site. And what that will do is it just brings you to a web page. Oh my gosh, there's emojis flying. I didn't realize there were flying emojis. Anuva, did you know that there were flying emojis?
No, I didn't. Would you be able to paste the link in the chat?
Oh, yeah. Okay, so actually, PJ got it for us. Thank you so much. Here, oh, gosh. My thing is having a breakdown. I'm just going to type it real quick. Anytime I hover over someone's message, it's like, do you want to delete their message? And I'm like, no, thank you.
I believe if it's the same format as we did on our second preview, it's going to be like a Kahoot style. So we're going to have time for everyone to put in their answers, and then we'll go over the correct answer, and then we'll talk about it for a little bit.
Ohad, I hope I pronounced your name right. It's going to be 7 questions, and you'll be able to see where we're at. Right, not at quite the bottom left, but mid bottom left, or mid left bottom. There we go. That's where we're at. I can't believe I have fans. Love you guys.
There's not a leaderboard, but
yeah, part of our thing, we want y'all to feel confident, but we don't want y'all fighting each other either. So you get to see if you got it right, but we don't want y'all duking it out in the chat, please.
Oh my gosh, we have 213 people.
Okay.
Essentially over.
That feels like a majority of the people here, and there's a potential that not everybody. Oh well, we're still getting. Let's reveal the answer, and more people can join in a second. Awesome, 100%. What a start, y'all. Great work, everybody. I don't exactly have anything to say. Y'all got that.
Just remember
Yeah.
Avogadro's number. So, yeah.
It's on the formula sheet also, I believe. It was last year. Anuva, can you confirm that? Confirm? Okay, gotta confirm. All right, second one. What is the relationship? Wow. What is the relationship between the atom and the strength of an electron's attraction force? That one has longer answer choices. I will give you guys a
Sorry,
second.
do you also hear the music?
What?
Yeah, where's the music coming from?
Oh, it's coming from. Okay, you see how there's that volume meter? It's right next to restart quiz. Please don't hit restart quiz.
Oh.
No, don't hit restart. Okay, there we go.
Okay,
You
because I was
scared
like,
me
am I
hovering over that.
hearing this music right now. I was like,
Yeah, that was a little annoying.
scared me.
Uh-oh. There we go. Cool. It seems like the audience really wants us to keep the music. Can we get some music back on? I guess.
I got you guys.
Why did we put the? Oh my goodness, we are going insane on the main page. What is happening? There we go. We're good. We're good, guys.
Yeah, we're good.
Crowdcast is just having a little bit of a meltdown. Can we turn the music up a little bit more? I don't know if it's just me. I can't super hear it.
I can hear it real loud.
Oh, okay. Don't turn it up then.
Okay.
Oh, well, okay. We're getting no music now. Anyway,
no music.
okay. I think we might be ready to reveal answer. We've just been sitting here for a while.
Yeah,
Right.
okay.
All right.
Okay.
That's a pretty good lineup, y'all. So C was the no. Okay. So the reason that C is not quite correct is electron is going to be your negative particle, right? So as the number of electrons increases, that's actually going to repel you, or not you, repel atoms from other electrons. It's going to actually send you away from every atom around. No. So this one, I think it might have been slightly a matter of just reading through it very quickly. Trust me, I'm definitely guilty of that. But as the number of electrons increases, I think that's the shielding effect, where that's actually going to make your attraction become smaller. Hey, can we scroll up for just a second? Perfect, thank you. So yeah, as the number of protons increases, the electron's attraction is going to increase because of the positive and then the negative. Okay, I will re-put the code or the link in the chat real quick. If we can get on to the next question, please.
Yep.
I'm so good at typing.
Okay, for number 3, we have electronegativity is greatest at the blank blank of the periodic table. So just remember Jahangir's periodic table that he had physically and where he's pointing.
Y'all are speeding through this.
Yes, remember that electron Riz.
I love the chemistry Riz in this chat. It's so good.
Wait, what's the best Riz we've been hearing? Because I didn't see much.
Oh
We
gosh,
had
I
a
wish
lot
I
of
had a way to
Riz
see
earlier.
it.
Everyone should like drop their favorite AP Chem pickup line that they
Oh.
want to tell their AP Chem crush.
One sec, actually. Ohad, I noticed you're talking about the TI-84. So fun fact, if you'll be joining us on night 4, we'll be talking about a bunch of the different functions that come with your calculator. Some that personally saved me during that exam.
I think if you go to programs and then it should say like periodic table, then you can like pull up the entire periodic table on your TI-84. I know it's on the plus CE. I don't know about any other calculators, but yeah.
Okay.
my
Oh my
God.
gosh, that's a list. I'm not reading those out loud right now. Maybe
Do
later
wanna
if we have
reveal
more
the
time.
answer?
Yeah, reveal the answer for us. Let's go. All right, again, a very, very solid answer. So trying to think of the best way to help remember. Anuva, do you have any advice to help remember top right?
Just remember fluorine got that Riz, and
Yeah.
fluorine's in the top right corner. So
Fluorine got that Riz, guys. Just you're sitting at your AP exam. You got an FRQ about electronegativity. Just remember, the closer the elements are to fluorine, the more Riz they got. For fluorine is our Riz king. All right, next question, if we can. Which of the following is a homogeneous mixture? Now, I know this is going to be talked about a little bit more in the next unit. However, technically it is a unit 1 or 2. I want to say Unit 2 thing. So if you guys miss this, don't stress. I'm going to be helping you out next Unit 2. But I kind of wanted to get a feel, see how long we had to spend on that one slide.
Oh my God, these pickup lines are so good.
I
Oh
know.
my God. I
Yeah,
want to talk about
negative
this one.
delta Riz, like,
Why is someone? I'm not even trying. Oh gosh. How?
then that means it's like more favorable. We'll go over that
Tomorrow, I think. Is that today or tomorrow?
tomorrow. That's
Okay,
Unit
tomorrow.
6, I think.
We got that delta. We got that delta Riz tomorrow.
Milk before cereal is a crime.
Holly, are you sure that's allowed by College Board?
Wait, let me see.
I don't want to argue with anyone in the chat, but I feel like since that's a program that's being added, I feel like that's not allowed by College Board.
I feel like
wouldn't
it's not
go into-
allowed, but we
Okay,
don't
like
worth it, but
I would say that that's a risk I personally wouldn't take during the
Yeah.
AP exam.
also I believe like sometimes like your proctor will make you like clear your RAM, but
Yeah, it's really I would not risk anything that could get your score disqualified, because I promise everyone around you is going to be so angry because they're going to be terrified that their score is going to be canceled. I'm saying that from experience. Anyways, can we reveal the answer? All right, okay. That's a really good distribution. That gives me a good sign. We'll talk about it a little bit during Unit 3. I got you guys on that, but honestly, an amazing start. Amazing start. Can we go to the next question? TI-84 is allowed. I apologize. I was not trying to say TI-84s aren't allowed. I'm saying writing notes in your TI-84 I'm not so sure about.
Okay, so for number 5, which of the following substances conduct electricity in the solid phase? So we have a bunch of molecules and like their chemical composition.
Also, I just want to make sure, since we're talking about calculators and since y'all are very good at multitasking, apparently, genuinely, like, wow. I want to make sure that you guys know this year, you are allowed to use or calculators on your multiple choice section. That was something that's completely different from last year. However, this year, if you're wanting to use your calculator for the multiple choice, totally cool. I have not seen anything about how it's going to impact the difficulty of the test. My prediction, knowing how AP test changes have gone before, they're probably not going to change the difficulty of the material itself, but they might give you more difficult numbers that would be hard to hand calculate. Eddie, you are good to use your calculator on the multiple choice this year, though, so yay. I also, not to go off topic, I think the SAT might be changing, so you can use a calculator for all of it now. Anyways, almost everyone's answered, so I think it's time to reveal the answer. All right, awesome. Very good start once again. Very good start. I can understand how B got picked a few times, just knowing that the ions allow electricity to be transferred once they're dissolved. However, potassium bromide itself does not necessarily conduct electricity. It's whenever those ions are loose and free in water that
Yeah.
it becomes. Why are
just
we sending eggplants?
Just remember that like in the question it says in the solid phase, so it's like considering like if any of these molecules are like solidified by themselves rather than like, for example, potassium bromide being dissolved in an aqueous solution.
Okay, next question. Sorry, I was answering a quick.
No, you're good. What bond order is this? 6 electrons involved in a bond.
So this one wasn't necessarily explicitly gone over the notes. This one actually I more put down in this quiz in case we need to go over in a future night, because I believe it gets talked about a little bit later. But we wanted to make sure that, hey, we didn't need a full section to talk about this for a minute. Why not KBR? Like I said, it's set in solid state. Anuva went over this way better than I did. But KBR, it said specifically in solid state. Electricity will transfer through it whenever it's in aqueous, so it's a liquid solution. However, as a solid, it will not conduct electricity. Trying to wait for a few more responses.
Yeah, and also zinc is a metal, and then
Yeah.
yeah.
Okay, so Adam, why does zinc conduct as a solid? I'll be talking about that a little bit whenever I'm talking about the different kinds of forces. However, to give a little spoiler alert, I suppose, it's because the way electrons work in metals is they all kind of share this weird one cloud. Yeah, I'm in my Singer arc, y'all. They're in this one shared cloud, basically, where they're all kind of simultaneously share. Yeah, they're delocalized. That's the nice way of putting it. I was just gonna say they all get shared around, and yeah. I believe that's true of all metals. Anuva, can you confirm?
I believe so.
Okay. And it looks like everybody's answered. In fact, I don't know how. It looks like more people have answered than we have, but sure. Okay, awesome. Okay, awesome, perfect. Can we
Yes,
explain
so
this a
just
little bit?
remember that like each bond is 2 electrons. So then when you have a triple bond, 3 times 2 is 6. So yeah. Don't select second order, guys. That's
Yeah, that was. We have to put 4 options. So if you, yeah. Okay, next question and last question, guys. We gotta make it count. Don't cheat, but we gotta make it count. Now this is a Unit 3 one specifically. This is my little transition question to get into my funky stuff. Oh my gosh. Hey guys, okay, seriously, do not spam the chat, please. It makes it difficult for moderators and us to read what's going on, and it makes it difficult for people to continue conversations. Thank you. Sorry to harsh on the fun, but it makes it very hard for me to follow what's going on, and I'm a very distractible individual if you can't tell.
Yes, we're getting a 5, guys. We got this. And again, I know we did it like really fast, so the slides are going to be made available and the recording is going to be made available after this stream is over.
Yeah.
The Riz is coming back.
For the people debating what inner versus intra is, don't worry. I got a very good comparison to make for y'all whenever we talk about this, and it involves my lack of ability to drive even at the ripe old age of 18. Lucy, I don't know what 5555555 please exclamation point means.
Get a 5 on the exam.
Oh, okay, that makes more sense. That makes more sense. I was trying to like follow like, oh gosh, the 55555.
Okay, we can reveal the answer now.
Oh yeah, reveal. All right, okay. I'm not. I knew it was gonna be between these two. Don't worry, I'm gonna help you guys remember it. Y'all are gonna think of me during the AP exam when you're questioning which one is which. But we got you. In fact, I'm not even gonna explain this one yet because I'm quite literally about to in the first 2 slides that I present. Okay, but awesome. Ending quiz. Do we see the results at this point? Can we get an end quiz? We got an end quiz, guys. Awesome. Y'all did absolutely amazing. Super proud of all of y'all. If everybody is cool and ready, I am happy to go in and start doing units 3 and 4 as your unit 3 and 4 specialist.
Okay, and then I'm gonna stay on stage, but I'll be here for unit 5.
Yeah, Anuva's our unit 5 expert. But I like having a buddy, you know, and
I'm here for moral support.
we're here to talk about chem. There we go. Thank you. Anyways, Unit 3, Intermolecular Forces and Properties. Now, this unit is going to be your biggest, most tested unit on the exam. In my experience / opinion, I think this is more heavily tested during the multiple choice section. However, you are very, very likely to see a couple questions on the FRQ. So we're here to help make sure that you guys got a good grasp on this. It's up to 22, so don't stress. It might not necessarily be 22. And honestly, if this unit is 22% of the test, that might be to your benefit. That means a little bit less math later on. Why are we throwing phone numbers in? I hope we're not doxing anybody, but okay. Anyways, next slide. Let's go. Awesome. So first, we're going to start with our intermolecular forces. These are going to be the forces that hold molecules together. Now, you're going to notice between dipole-dipole forces and hydrogen bonds, there's going to be an arrow. And we're going to get to that in a second. But we're going to go in order. We're going to go for order. Yeah, let's not drop phone numbers in the chats. Thanks. Bye. So first, we're going to be starting off with our London dispersion forces. Now, I think this one's kind of funny because despite having the longest name character-wise, I think, don't quote me on that, don't do the math, it looks like it's the longest. It's 3 lines versus 2. It is the weakest type of IMF. It's actually the only type of force between 2 nonpolar molecules or noble gases, but to make a very clear point right now, it will always exist between all molecules. That is something that is going to be tested on. I always, every practice test I did and on the actual AP exam, you will see a question that says, what kind of intermolecular force exists between these two? And it will always try and trick you by giving you one that has the strongest force but doesn't mention London dispersion forces. Unless it specifically says what is the strongest force between these two molecules, always make sure London dispersion force is in the list. However, the strength of these London dispersion forces is going to increase as the size of the molecule increases. So something like glucose is going to have stronger London dispersion forces compared to methane, I guess. Yeah, let's hold off on Discord or phone numbers. Okay, thanks guys. Love y'all. So our second strongest one is going to be your dipole forces, and we're going to get into the hydrogen bonds in a second. But just to start off a little bit more broadly, these dipole forces only exist between 2 polar molecules, which results in a slightly stronger force than an LDF. And this happens because the opposite partial charges on opposite ends of the molecules. So basically, if you'll look at the diagram here, I tried to kind of show it, and obviously it's not going to be you have a negative thing here and a positive thing here. It's almost more like a gradient as you go, just due to the electron, oh my gosh, due to the electron cloud and stuff like that, the bonding, bada bing, bada boom. But the slightly more negative side is going to be attracted to the slightly more positive side. Which brings us to our hydrogen bonds, which is the exact same concept, except different because of the electronegativity difference that comes up between hydrogen and then specifically nitrogen, oxygen. Uh-oh, we got someone on stage that I'm going to put away. Specifically between the strong electronegativity difference between hydrogen and then nitrogen, oxygen, and fluoride. Now, these Van der Waals forces, I've never heard that. However, if it's the same thing, I would check online. I can't personally answer to this because I always learn them as London dispersion forces. But yes, I believe if they're the same force, you can use that term. But just keep in mind, you might see London dispersion force. Anyways, back to hydrogen bonds. The way I personally like to remember this is no ostriches fly. I don't know if this is scientifically accurate. Please don't question me in the chat. I will be sad if y'all question me in the chat. I'm seeing a lot of fun as well too, like fun. Make sure you know it's an O instead of a U, because if you say uranium as part of the hydrogen bond, you're going to get a couple of points off. Hate to tell you that. But yeah, just keep in mind it is a kind of dipole force. They're the same, which is why I use very similar models between the two to make sure I can highlight why this is the case. And then finally, our last one is going to be ion dipole forces. Oh, we're getting some question marks in the chat. I can't tell why people are question marking. Well, I hope I figure it out. Feel free to put it in the Q&A section if you need. So ion dipole forces are going to be your strongest type of IMF. So this is going to specifically occur whenever a cation or an anion is attracted to the negative or positive end of a dipole, respectively. So more specifically, or not, yeah, respectively. So a cation to the negative end of a dipole or an anion to a positive end of a dipole. Now this occurs in a very specific situation where it is a mixture of ionic compounds and polar molecules. So you're not going to see this super specifically. Una, I hope I'm pronouncing that correctly. I believe you want to take VSEPR into account. However, if you can have a couple of like major molecules, the ones that are pretty frequently, okay, we're getting some questions answered. I think I'm going to let chat people handle that one just so I don't keep getting distracted. But yeah, this will only occur in your mixture of ionic compounds and polar molecules. Can we go to the next slide? Intramolecular forces. Now here's the point where I make the little anecdote thing to help you guys understand the difference between inter and intra. So your intramolecular forces are going to be forces within a molecule that hold your atoms together. It's going to be stronger than your IMF, partially because of how close they are. However, how do you remember which is which? I use the interstate system. your interstate highways are going to be from one state to another state. It's not going to be within a state. It's going to be between your two states. Why this is the one that works for me, I have no idea. I'm 18 years old and I just have my driver's permit. But it works for me, and hopefully it'll work for you too. Now, the question is, yes, higher molar mass is going to be your stronger London dispersion force. Why are intramolecular forces stronger than your IMFs or your intermolecular forces? So your greater attraction between the protons in the nucleus and the electrons in the electron cloud are due to Coulomb's law, which states that the attraction of two charged bodies is proportional to their charge and inversely proportional to the square root of their distance. Which is basically to say, feel free to correct me if I'm incorrect, Nuva, but the charge of your body, so in this case, it could be an atom, it could be an ion, believe it could be a molecule in terms of Coulomb's law, not in terms of intramolecular forces. The charge of it's going to be more important than the distance. However, the distance definitely does have a major impact. Okay, we're getting a thumbs up. That means I'm doing something right. So awesome. We're going to go to our next slide now. You know how I said we're going to go over this more? Here we go. We're going over this more. So our first type of solid we're going to be talking about. And this one, in my experience, this isn't going to be super heavily tested, but I would still keep it in mind because what I have seen most frequently is usually you're going to get a few questions about covalent networks and or metallic solids, and then you'll often see one or two about ionic solids. Maybe you'll see a molecular. That one I haven't seen as much. AP chemistry is greater than permit. So true. Yes. Anyways. So our first molecular solid, our first solid is a molecular solid. Now these are going to be specifically between atoms or molecules, and these will always have LDFs, might have dipole, might have hydrogen bonding. These solids are fairly soft, they have a low melting point, and they're bad conductors. You'll notice that all of these are bad conductors except for metallic. And I will talk about the different kinds of intramolecular forces that explain that when we get there. Isn't molecular the same as covalent? Yes, I believe so. However, covalent network is separate. That has to do based on the shape of how they bond together. Yeah. There we go. Thank you. I don't know how to pronounce that name. I apologize. So some examples of this is going to be your argon, your methane, your sucrose, and your dry ice, which is a form of carbon, I want to say. I wasn't tested on dry ice. I don't know. Okay, cool. Yeah, thank you for the refocusing in chat. So this one, if it doesn't fit the criteria of the others, good chance it's going to be your molecular solid. Your next one's going to be your covalent network, which is a type of molecular solid, but it's very structured and organized. And what's going to happen in that case is you're going to notice it has very straight lines through the pattern. It's not going to be kind of jumbled. You're going to have a very strict pattern to it, which is going to be your network of covalent bonds, specifically a network. And these have your LDFs, might have your dipole, I believe, but these will also have your covalent bonds, and that's very important to keep in mind. These are very hard, very high melting point, and that's because of the structure. It makes it, oh, okay, awesome. Frozen CO2, thank you. And then they're also bad conductors, and that's because their lack of free-floating electrons. And these examples are going to be your crystals. Diamond and quartz are some of the first that come to mind. Your ionic solids are going to be the solids that break up into positive and negative ions. And these are bonded with electrostatic attractions, which is basically, hey, I'm positive. Hey, I'm negative. Mwah. They have their own Riz, They have Riz for each other. But they don't have Riz for, positive and positive and negative and negative. So these are going to be hard and brittle, and they're going to have a higher melting point, but they're also poor conductors. Anuva, do you happen to know off the top of your head why those are hard and brittle?
No.
Okay, sick. I apologize. I'm also not 100% sure. If we can have someone in the chat, one of our people, check that over real quick, that would be absolutely amazing. And then finally, we're going to have our metallic solids, which are specifically going to be atoms, metallic atoms, which are going to have the metallic bonds, which, as we talked about beforehand, are going to be your free-floating electrons that are kind of being shared between. Yeah, I'm going to guess it's because the lattice structure is well for ionic. So properties, varying hardness, because it kind of depends on the atom. You can think of something like mercury and gallium versus iron. And I guess steel's a type of metallic solid because it's a alloy. There we go. But yeah, like I said, these are going to be your metals, your copper, your iron, your aluminum, etc., etc. Okay, next slide. Okay, perfect. Now, this is going to just be talking about your broad traits of your solids, liquids, and gases. If this chart isn't your study guide, which I'm almost positive it is, but if it isn't, feel free to add it in. This is a very, very good one too. Wow, y'all are good. Thank you for the explanations in chat. Thank you. And to answer Amelia real quick, an alloy is just going to be a mixture or a homogeneous mixture of two different kinds of metals. So your IMFs, you're going to notice with all of these that there's going to be some trend either left to right or right to left in terms of strength. So the strength of your IMFs is going to be strongest with your solids. And if you think about it, this makes sense. They're the closest together. They're very rigidly held spot. And usually they're pretty rigidly held spot because of the IMFs. But with gases, they're crazy. They're going all over the place. They're kind of like me right now trying to explain this all to you. They are going all over the place. And because of that, so much space is between them that there's not really a ton of IMFs in between in standard conditions. Ashvik, I apologize if I pronounced that wrong. We're going to be talking about that in a couple later nights, but we can, if we have time at the end, we can talk about that a little bit more. With density, we're going to be thinking about the strength of the IMFs trends again. If you think about it, if those IMFs are strong, that means they have to be close enough for them to be strong, because remember about the relationship of distance. If they're close together and they have those strong IMFs, that means there's going to be more of them in one space. And then again, with gases, they're shooting all over the place. There's a lot of blank space in between comparatively to solids. Fluidity. This one, your brain immediately is like, oh yeah, liquid's going to be the most fluid because it's a fluid. It's more fluid than a solid. You wouldn't be wrong on that front. However, which is IMFs? Faith, can you elaborate real quick? Fluidity. However, think about how free moving that the gases are. Because of their ability to not necessarily be attracted to each other and not locked in place, they are even more fluid than liquid is. And then compressibility. This is the one that kind of breaks the trend, but also not really. You can still kind of keep the trend in mind. Solids and liquids, they're already so close that it's very difficult to compress them. If they're close enough to the IMFs, it's very difficult to say that they are not close, or that they are not close enough to be able to be, or oh gosh, okay. They're already so close that it is difficult to compress the atoms or molecules even further. However, with gas, you'll think about with pressure and volume and all of that, and we'll kind of get into that with your ideal gas law. You can squish those together more, and that will actually change how they interact with one another. So I think that's actually what we talked about. Next is our ideal gas law. If we can get that next slide. Perfect. Now, you'll notice these arrows, and we'll get into that in uno momento. But just to go over some of these laws, I don't believe you have to know these laws by name, only by concept. I want to say that is true of most every law that you will learn in AP chemistry. If you understand the concepts, you don't necessarily have to know them by name, but knowing them by name can help save you if you're struggling to explain it on an FRQ. So it's good to know them. However, if you're struggling, just explain it well, and you should be okay. But you'll notice here that all of the top laws, Boyle's, Charles, and Guy-Lussac's law, combine into the combined law. That's why it's the combined law. It's because they're combined. Wow. Whoa! Are these on the formula sheet? Nuva? Yes, they are. Is it combined law, or is it all three of them? Or all four, rather?
I know the ideal gas law and the combined law are on there.
Okay.
But technically, all of the Boyle's, Charles, and all of them are in the combined law. So
yeah, I was gonna get into that. So even if you forget the other three, if you are given a question that only gives you pressure and volume for example, or Charles's volume and temperature, or pressure and temperature, you can still use the combined law. Just disregard whatever information isn't given to you. You have to have at least two of them to be able to use combined law. But if you think about it, if two of them are the same, if we're assuming that two of them are the same, which you would in the case that combined is not on the formula sheet, okay. most of the time you can defer it from ideal gas law. However, having it memorized is a very good idea. Yeah, PV over NRT does replace all of them, I think. I think you are right about that. But you can assume the same, and then if you think about that, you would just be changing like the proportion, which means you can disregard it. You would just be changing the number, but the proportion of each would still be the same. So for the exam, you probably wouldn't know your combined gas law just for ease, and then your ideal gas law, Pivner, which is the very big important one. That one is on your formula sheet. Now you'll notice over here that on the far bottom left is going to be what each of those stand for. That is going to be covered on your formula sheet. However, there are times wherever a letter can stand for multiple things in different situations, so I really wanted to make sure that it was clear on this slide. R is going to be your universal gas constant, which as of last year was in fact on your formula sheet. You have to kind of look for it. It's not at the top, but it is there. But you do have to keep it in mind anytime you're using ideal gas law. And that's good to find, like, hey, you have all this information. Guys, can we stop throwing Discord in the chat, please and thank you? Anyways, they have R in tours too, right? I don't remember it being given in tour, but it might be. But I think you might be able to convert it, but it would take a minute. I last year never saw a question where I need to convert the universal gas constant to tour. Trevor, if you need friends, we can talk about it in the Q&A section. But right now we're going over focused info. But yeah, as terms of the rest of those are going to be pretty standard. Anytime you see N, it's probably going to be your moles. Anytime you see T, it's going to be your temperature, et cetera, et cetera. Conversion should be on your formula sheet as well, but having them memorized also helps you. On to the next slide, still talking about your gases. Dalton's law of partial pressure. This one is a little bit weird in my opinion, but what it's basically saying is that the pressure of a gas in relation to a specific gas within like a mixture of gases is directly proportional to that number of moles of that gas in relation to the total number of moles within the closed container. This has to be in a closed container. You can't go like in this infinite space that never. Elias, if you don't mind me asking, what you score on the AP Chem exam? If I don't say a 5, will y'all trust me less? Realistically, I did get a 4. However, that was a COVID year and I got sick a few times, so it was a little difficult for me to study. However, if I got sick like 3 times for 2 weeks, yes, y'all will trust me less. Oh, okay. Okay. Anyways, I did get a 4. I was sick for like 3 sets of 2 weeks though. So if I can get sick for like a month and a half total and get a 4, y'all totally got this. But anyways, going back to Dalton's law of partial pressure. Uh-oh, people are side-eyeing me. Yeah, it's kind of an excuse, I'll be real. But part of this is going into the idea that, as you kind of talked about, I'll get into hardest material at the end of this. Hardest, wow, okay. The total amount of pressure of each gas, it will add up cumulatively, it'll be the sum. So if you have 2 atm of hydrogen, 3 atm of oxygen, and 1 atm of nitrogen, you're going to have 6 atm of pressure in that closed container total. And this kind of goes on to that idea. It's basically stating that there's a direct proportion between the moles of that specific gas. There's not a 7 on the... Okay, whatever. Anyways. Basically saying that that rule still applies with the moles of gas as well. Now, the kinetic molecular theory, I want to say that is definitely on the formula sheet. It doesn't have to be memorized, but it is a foundational building block when you start getting into stuff like Unit 5 especially, but just understanding how gas interacts with itself and what happens when they hit each other and feed and such and such. Going into the next slide, we are going to be talking about diffusion from ideal gas law and then Graham's law of effusion. So in what situations do gases deviate from the ideal gas law? So in high pressures, whenever you got your really close gas or molecules or atoms really close together, and then a low temperature, which decreases the speed, can cause gaseous atoms to become more attracted to one another because those IMFs are going to be able to have a greater impact with one another due to the fact that they're able to get closer together. Gas particles can make up a significant proportion or portion of the gas sample's volume in the case of high pressures. So that kind of leads us more gas stuff, grams rate of effusion, which is going to be your rate 1 over rate 2 equals the square root of your molar mass of the second gas over the molar mass of the first gas. So effusion is the average path a molecular particle can take before hitting another particle. So this is the formula that you use. I don't know if we can ban individuals from using the chat. I apologize.
By the way, just because we're hitting the halfway point, we're going to focus on the material, and then we'll read questions a little bit once we get to the quiz after Unit 4.
Yeah, after Unit 5 is going to be your quiz.
Yeah, so we're just going to focus on the material for right now, just because we're running a little bit behind on time. And there's moderators in the chat that will help answer questions that are in the chat, just to make sure we have enough time.
Okay. Thank you so much. So what this law of effusion is basically saying, due to the inverse relationship between the molar mass and the rate of effusion, the speed or the path, gas molecules that are lighter will travel faster than a heavier gas molecule. So this states that the rate of diffusion or effusion is inversely proportional to its molecular mass, its weight, and its speed in the meantime. So going on to the next slide, we're going to go off to another path now, once that slide changes. There we go, mixtures. Technically still related to gas, but I know y'all are going to say that's not it. Isha, the formula I just showed before, which is going to be your rate 1 over rate 2 is equal to the square root of molar mass 2 over molar mass 1. I'm not sure if that's on the formula sheet, Anuva, yes or no? Shrug. The formula sheets are online if you want to take it a look over. I don't think it necessarily has to be memorized. I think you should know it because it could be asked on the FRQ, but it's not a guarantee. I personally would. So mixtures. This is kind of broader concept of solutions that we'll be talking about in a second. AP Chemistry, the mixture typically is going to refer to specifically a heterogeneous mixture, where different materials are able to be easily separated without the use of chemicals. So some of the examples I like to use are like soil and trail mix, things where you can separate the little parts and make little piles very easily without pulling out like a flamethrower and sulfuric acid. You know, we don't like having to throw out flamethrowers and sulfuric acid, but you know what? Sometimes it has to happen. There are homogeneous mixtures as well. They are uniform in composition. There's very little variation throughout the mixture, so it makes it very difficult to see its individual parts. However, in the case of AP Chemistry, these are typically going to be referred to as solutions because they're usually aqueous. I want to let you guys know in case it's a little different, or they try and throw you a curveball. However, typically it's going to be called a solution if it is a homogeneous mixture. Next slide to talk about solution. Yeah, put away the flamethrower, kids. We can't be pulling those out right now. The solutions are going to be your homogeneous mixture where particles are evenly mixed and the solute, which is the substance that is being dissolved, is uniformly distributed within this solvent, which is the substance that does the dissolving. One way, because I tended to struggle with remembering which was the solute and which was the solvent, just remembering that water is your universal solvent and knowing that in aqueous solutions, you're throwing things into the water until it cannot hold anything else in said water, that'll tend to help you at least keep some idea. So we tend to talk about solutions in a liquid state. However, they can exist in all three states of matter. The solids with the metal alloys, which was what someone asked about in the chat earlier, which is going to be your uniform mix of two different metals. I believe steel is an example of this with iron and zinc or copper or something like that. Liquids, bunch of examples. Every solution you're going to have to do math on is probably going to be a liquid solution. Might be gas, probably going to be a liquid solution. It also can be a solid solute dissolved in a liquid solvent like sugar water. And then gas, great example, air. But you're usually not going to have to talk about like solution stoichiometry in the case of gases or in solids. So going on to the next slide. Okay, do we need to know about ion-induced dipole or dipole-induced dipole forces? I don't remember if I had to learn it, at least by that name or not. Anuva, do we have to know about ion-induced dipole?
I just answered in the chat.
Oh,
you need
perfect.
ion
Okay.
dipole and dipole.
Okay. Oh, so it's another way of saying that. Okay.
That's what I think, but I
Okay.
could totally be wrong.
Thank you. So representing solution composition, I'm sure at this point in the class y'all know what molarity is. However, just in case, especially for those of y'all who are self-studying, it might be a little bit weird for on molarity versus molality. Molarity, which is the one you have to know. Don't let your AP chemistry teacher tell you otherwise. You do not need to know molality. I got that bashed into my head for no reason. It does not come up on the AP exam. If you take like Chem 2 or 3 in college, it might. But for AP chemistry, you're good. Don't stress. So molarity is going to be your number of moles of solute dissolved for every 1 liter of solvent, which makes your formula M equals moles of solute over liters of total solution. You might get a question. Guys, stop throwing Discord links, please. Seriously. Anyways, for example, a solution that contains 24 moles of hydrochloric acid dissolved in 2 liters of water would be calculated as the molarity equals 24 moles of HCl over 2 liters of H2O equals a 12 molar hydrochloric acid solution. Ouch, ouch, that would hurt. Gonna be honest. So, and then dilution, which is basically saying how many moles would be in how many liters if you were to add this much water or were to boil off this much water, is represented using M1V1 equals M2V2, where M1 and V1 are the molarity and volume of your original sample, and then M2 and V2 are the molarity and volume of your diluted solution. You're always going to be told your target volume or your target molarity, but you will not be given the other, and you can use that to find your proportion and then divide it either by the molarity that you're given or the volume that you're given. Yes, molarity and concentration are the same thing. Going on to the next one, we're going to give you a little sneak peek for a future unit. Acids and bases. Whoa. Color is not important. I just wanted to use the 5-able colors because I think they're really pretty. Acids are not purple. Bases are not always blue. Acids are not always purple. I don't know why I just said they're not purple. So acids and bases are electrolytes, or substances that break up into charged ions when dissolved in a solvent and are capable of transporting an electric charge because of it. So whenever people... Guys, please don't cuss in the chat either. There we go. We're not at Unit 8 yet. Y'all are aggressive about acids and bases. Jeez. Okay. Good news. Air is not heterogeneous because it's not able to be easily physically separated. Acids and bases are electrolytes, which are broken up charged ions in a solvent. So whenever we were talking about KBr not transporting electrons earlier, this is what it was talking about. It can transport electricity whenever it is in an aqueous solution, but as a solid, it cannot. Acids are going to be your proton donators. They're increasing the concentration of aqueous hydrogen ions. However, bases, there we go. Proton acceptors, increasing the concentration of aqueous OH- hydroxide. An acidic solution will have a greater concentration of H+, which is just a proton basically suspended in some water. Because, a hydrogen atom without its electron is straight up just a proton, I think. And as hydrogen atoms alone only have 1 electron, but the positive charge demonstrates that the 1 atom has been stripped from the atom. Basic solutions, on the other hand, have a greater concentration of OH-, which would really want an H+. Color for compounds. I think it is good to know it will not be heavily tested, and cause solution to be more negatively charged due to that excess electron. Going to the next slide, talking about the separation of solutions and or mixtures. So we're going to go over 4 big ones that you really have to know. These are the ones that are going to be very heavily tested. In my experience, I have not seen any other ones other than like very hyper-specific tests. Starting off with evaporation, you guys probably know this one. This is when you got the salt water and you don't want the salt in your water. You make the water really hot and then the water just evaporates. It's bye. Now you just have some salt. This is how you get your sea salt. So this is the process where the solvent is boiled and converted into gas in order to leave the solute behind. Typically done with a solid solute, though, something that's not going to boil off at any reasonable temperature that a normal human will be able to get it to. Filtration, on the other hand, is whenever you run that whole solution through a porous barrier. The liquid solvent passes through the barrier, but the solid gets trapped in the filter. This is typically not going to be what you do with a full-on solution. This is going to be more with a mixture that has like sediment stuck in it, or floating bits of material that aren't fully dissolved. We are going to be going over chromatography, don't worry. So you're not going to typically see this with like your fully liquid aqueous solution. However, if you do have like small pieces of something, very good way to separate the pieces from the liquid. Next slide, please. Yeah, see, told y'all we got chromatography. I got you guys. So distillation. This one's like a weirder form of evaporation, in my opinion, because tends to be what you do whenever you have multiple liquids, so a liquid solvent, then a liquid solute, or multiple liquid solutes even. So your solution is going to be very slowly heated. So one of the compounds within the solution boils out and then recondenses into another beaker. But you have to be very careful with this temperature. And backstage. Okay, yeah. Going to basically go as the speed of the the weakness of the IMFs goes. Chromatography, on the other hand, and I can see a lot of people are struggling with that, is going to be a small amount of your solution is going to be added to a strip of chromatography paper, and then using capillary action based on the weight of the different solutes, is going to be going up different parts to different amounts, and the solution is separated based on both the affinity of the paper and most frequently with the AP test is going to be going up based on the weight of the compound as well. So going on to the next part is going to be talking about your solubility. There's going to be three types of saturated solutions. You're going to have your supersaturated, which is your solution where more solute is dissolved within the solvent than is typically possible. That's going to happen. Whenever you heated up your solvent while adding the solutes and then brought it back down to a typical room temperature. This can cause, if you have enough of a supersaturated solution, crystals to form within the water. Your normal saturated solution is just whenever at a specific temperature you've added as much solute as can be added to the solvent. No more, no less. Undersaturated means you can add more solute at the end. So there are going to be 6 major factors that are going to impact your solubility. Your polarity, a polar or solute will dissolve in a polar solvent, and a nonpolar solute will dissolve in a nonpolar solvent. Pressure, as you increase the pressure of the gas, the collision increases and increasing the solubility. More typical with gases, but can occur with liquids. Temperature, an increase in temperature puts a stress on the equilibrium condition, which we'll be talking about more tomorrow, and it causes it to shift to the right, though. Your concentration of solvent, increasing concentration of reactants will increase the frequency of collisions between 2 reactants. Presence of other substances may react with the ions, increase collisions, add some more extenuating circumstances. Basically, you've already added some stuff into your solvent. And then surface area, whenever you have a greater surface area, your solute of particles is increased, and then the solute is going to dissolve more rapidly within your solvent. And then next slide. So this one isn't going to be tested as much. However, you will likely see a question or two about it on your multiple choice. This is your Beer-Lambert formula. This is going to be talking about light. So your amplitude is going to be your vertical height of the wave, and this is going to be typically seen on the graph. Your wavelength is going to be the length of one period. So it's going to be the time that it hits through 0 twice if it's a sine graph or a cosine graph, for example, which is going to determine your color. And then your frequency, that is going to be the number of waves that pass in a fixed space. So a longer sine or cosine wave would be maybe half in the fixed space compared to 2 times in the fixed space. So this formula over here in your right-ish area is going to be capital A equals EBC. A is going to be your absorbance. There's going to be no unit to this. E is going to be your molar absorptivity of the solution, and L over moles times centimeters. B is your path length in the curvette in centimeters. And then C is going to be your concentration of the substance. Most of this information will be given to you. Typically, you're just going to be looking for one of those. The Beer-Lambert law is a linear relationship, which means the absorbance of the solution is directly proportional to the concentration of the substance, which means if the concentration of the substance in the solution doubles, the absorption will also double. And that should be it for Unit 3. Awesome. And then Unit 4, I believe, is going to be a lot easier because it's going to be your overview of a lot of the future units. It's going to give you your strong foundational base. So going into the next slide, we have 5 major types of reactions. You have your synthesis, which is going to be 2 things coming together to make one thing. Your decomposition, which is one thing splitting apart. And then your combustion, this is probably the weirdest one. This is when you have specifically a hydrocarbon, which is a carbon and a hydrogen molecule, and then oxygen, forming to create carbon dioxide and water. So for example, the combustion of methane is going to be your methane working with your oxygen, reacting to make carbon dioxide and water. Single replacement is going to be basically when one of the things in a bigger molecule switches out for another one of the atoms. And then double replacement is going to be whenever you have 2 molecules and then the cations or the anions switch between the 2 of them. Single replacement is going to be your most common, common type of single replacement is going to be your redox equation, which we'll talk about a little bit later. Our next slide is going to be talking about net ionic equation steps. This one is something that I personally struggled a little bit with, and this looks like a lot. This is going to help you out. I'm going to be helping you out showing an example in the next slide, though. So you're going to find out which compounds are soluble and insoluble, knowing your solubility rules, which we're going to talk about the major ones you need to know on the AP exam in the next slide. You have to balance it. Chances are it will probably already be balanced for an FRQ unless there's a question asking about it. I would always check, though, just in case, because they might not, just to throw you off. Write your complete ionic equation by dissociating the specifically soluble compounds into ions, and then omit the spectator ones, which are basically the ones that exist on both sides. We'll show that in a second. And then your final net ionic equation of the given reaction will be written out whenever you omit the spectator ions. You have to make sure to include the state of matter each compound is in, though. So we're going to show this in a second. Next slide, please. Okay, there we go. 2Ki aqueous plus PbNO3 aqueous converts into 2KNO3 aqueous to PbI2 solid. So if you're going to look in the top right real quick, College Board has stated that only the following solubility rule will be assessed on the exam. All sodium, potassium, ammonium, and nitrate salts are soluble in water. Sodium, potassium, you know, those are your alkali metals. Those are your ones with your excess or wanting another electron. So keep in mind your ammonium and your nitrate salts, which is actually brought up here. So you're going to see that I actually highlighted the ones that are soluble. And actually, the state of matter kind of helps you, but don't always rely on that. It might not necessarily be given. So the ones that are highlighted are going to be the ones we dissolve into step 2. So you have 2 K plus ions, 2 I minus, et cetera, et cetera. And all those italicized ones are just the bold ones broken up at this point into their separate ions. And then your PbI2 does not dissolve. It's not soluble in water. Now looking down here, you're basically looking for the ones that exist on both sides of the equation. You can notice that 2K plus exists on both sides. Your 2NO3 minus exists on both sides, but your 2I minus and your PB2 plus does not exist on the right side because that one did not dissolve. So you're going to omit the ones that exist on both sides, and you're going to get your final net ionic equation at step 4, which is basically showing that, hey, these are the ones that actually react to make something and don't exist as just an intermediary. All right, so our next slide going to be your acids and bases and titrations. This is going to be gone over a lot more in Unit 8. However, we're going to go give a brief overview real quick. I know that this is a little bit to go over, so I'll try and simple it down as much as I can. So titrations is going to be when you find your equivalence point for your acids and bases reactions. This is basically the point where you have found out that this much has reacted with this much of your acid or base. Equivalence point is going to be the point where the number of moles of titrant is added equals the number of moles of the analyte, which is what's being monitored. At the equivalence point, the reactants are completely consumed and the products are present in stoichiometric amounts. It indicates the end of the reaction right before the major pH shift, which you'll see in the graph. This will be gone more over in the acids and bases unit tomorrow. The end point is going to be when there's the visible change in the Erlenmeyer flask. Ideally, these should be the same. However, if you're using the incorrect indicator, your endpoint is going to be very separate from your equivalence point. So going over to the Bronsted-Lowry theory, that states that acids will donate an H plus ion or a proton, and bases will want to accept that proton. Acidic solutions will have an excess of H plus ions, and basic solutions will have an excess of OH minus protons. And those OH minus protons really want that H plus to make water. So going over acids and bases, and then conjugate acids and conjugate bases real quick, which will help us later on. Your first pair you're going to notice, and you're going to want to look for things that are slight shifts of itself. So for example, NH3 and then NH4 plus are quite similar. You're going to notice that that one just has an additional H plus ion. And then again, for the second one, you're going to notice that water becomes a base with OH minus for the second pair. The compound has an extra hydrogen on each side, and basically that's to say that the reactant is donating the hydrogen in the acid, and the product that has the excess hydrogen is the conjugate acid. The opposite is true for your bases. This is actually going to make your H2O the acid in the reaction, since it's donating its excess H plus to the NH3. Not typically what you see when you're thinking about acids, but however, in this case, your water is going to be your acid. And then your NH3 is accepting this additional H plus ion, which would make it the base. So in the products, in the opposite reaction, the NH plus would donate its proton to OH minus in the state of like equilibrium, for example, which would make NH plus, since it's donating its proton, the conjugate acid, and then OH minus the conjugate base. The way to remember this, I don't like thinking like, oh, well, it's this one over here, so you have to flip it over here. Just flip the equation around and then say conjugate. And then next little section of this unit, we're going to be doing our overview of oxidation reduction or redox equations. Can we get the next slide, please? Awesome, perfect. So there's a couple of ways to remember which is oxygen and which is reduction. But to go over quickly, oxygen is your process of losing electrons or increasing the oxidation state. The reduction is gaining electrons. I always like to use oil reg, where oil is loss, or oxidation is loss, and then reduction is gain. However, I've heard a lot of people use Leo says Ger, where loss of electrons equals oxygen, and then gain of electrons is reduced. So your oxidation numbers are going to be kind of weird. These are going to be your major rules that you have to know for the test, though. Oxidation numbers, your free elements, so your stuff like O2, just loose atoms, are going to have an oxidation number of 0 since there's no transfer of electrons between itself or anything. Neutral molecules elements, so anything that doesn't have a minus or a plus as a molecule must sum to 0. So monatomic ions have an oxidation number equal to their charge. So, for example, whenever you see a solution that has Cl minus in it, that's going to have an oxidation number of -1. Or if you're going to see a solution with aluminum +3, you're going to see an oxidation number of +3. Oxygen is going to be a -2, except in hydrogen peroxide and a peroxide ion where it's -1. Hydrogen is +1 except in metal hydrates, for example, lithium hydrogen or Ba hydrogen 2. Where it's going to be -1. It's much more adaptable than the alkali. And then your fluorine is going to be your -1. Other halogens are usually -1, but they can vary. And then oxygen numbers can be fractions, but it is very rare for the AP exam. So going into the next slide, which is going to be example. Perfect. Fe2 plus aqueous plus MnO4 minus aqueous goes into iron 3 plus and then Mn2 plus. So we're going to notice that there is going to be a loss of electrons. That's why it becomes more negative on the right side for your Fe2 plus to your Fe3 minus. And then this one over here on the right is a little bit weirder. You're going to have to go through some additional steps for this one. However, starting on your left with your oxidation, you're going to notice that since your reactant is going to be 2 plus, you have to add an electron to the right side, so that state is equal between the two. However, on your right side over here with your MnO4, you're going to have to add some water in order to account for those excess oxygen that is in your original reactants. So to do that, you just throw water in, and then to account for it, you're going to add some H plus ions on the reactant side. That equation is going to become MnO4 minus plus 8H plus goes into Mn2 plus H2O, or 4H2O. And then at that point, you can make an addition. You can add up your different states. In this case, you're going to have your 8 plus, and then minus, to bring you 7 on your reactant side, and then 2 on your product side, which neutralizes out to 5. And then you're going to notice that your number of electrons isn't equal. So what you're going to want to do is add coefficients to your entire side in order to make sure that those electron states are equal, and then you can remove them. So that will leave us with our final equation that's balance for oxidation reduction as the one at the bottom here that I'm not going to say out loud. But yeah, I hope that made sense, and that should be the end of our unit 4.
Okay, hi everyone. We got to unit 5, kinetics, my favorite unit. If everyone in the chat could drop how confident on a scale of 1 to 10 we feel about kinetics, and we'll get straight right into it. So if we can get, okay. So for the basic definitions, like what is kinetics? Kinetics is the study of reaction rates and the relation to the way the reaction proceeds. So it's mechanism. And we'll be going over what a mechanism is, which is a sequence of events at the molecular level that control the speed and the outcome of a relation. And then for reaction rate is the change in concentration of a reactant or product within time. And then we have 3 reaction rates we look at, which is the initial rate, which is the rate of the reaction at the very beginning, the average rate, which is the change in concentration divided by the change in time of the entire reaction. And then we have the instantaneous rate, which is the rate at a specific moment in reaction. So let's get right into it. So factors that influence a rate of reaction. So we have 4. So the first one is the physical state of the reactant. So first we have like the regular states that we have, the gas, liquid, or solid. And depending on these, how molecules are able to interact with one another. So gases, the molecules are more free flowing and will react faster compared to a solid, which are more solidified and then they're like more into their shape, like we went over for unit 2, unit 3. And then solids react faster when the surface area is greater. So for example, like in my AP chemistry class, we had like a reaction that went with like a solid versus a fine powder, and the fine powder reacts faster than the big chunks. So next we have the concentration of the reactant. So increased concentration means the increased likelihood of molecular collisions. So when you have more molecules, obviously you're going to have more collisions between those molecules, which will increase the rate of reaction. Then we have temperature, and I'm sure you guys all know if we have a higher temperature, then molecules have more kinetic energy. And then more kinetic energy means faster movements and more collisions with greater energy. And you need the molecules to have enough energy in order to react. And then catalysts, which we will also go over more in depth later, they speed up the reaction by changing the mechanism, by changing the activation energy and lowering it. And then the catalysts don't get used up by themselves, and they will always have a consistent concentration throughout the entire reaction, because even though they might get used up within like the middle elementary step, they will obviously come back in the end as the same concentration. So for an example, we have nitrogen dioxide. So we have NO2 gas going into NO gas and O2 gas. So the rate of reaction is proportional to the concentration of NO2, which is expressed as the rate law. So for the rate of reaction for this specific equation, it's K multiplied by the concentration of NO2 to the power of N. So K is the rate constant, which is independent of the concentration, but it increases with temperature. And something that is important is the Arrhenius equation, which I didn't list here because you guys do not need to know the Arrhenius equation. All you have to know is that the rate constant increases with temperature, and it's like a mathematical way of showing it, but you'll never have to use it on the AP Chem exam. And it's stated by College Board that you're never going to have to use it. And then for N, it's the order of the reaction. So it shows how the concentration affects the rate. So for example, if the order of the reaction is 0, there's no change when the concentration is changed. And for the overall reaction order, it's a sum of orders for each reactant. So say if you had 2 reactants, for reactant A, if the reaction order is 2, and the reaction order for the reactant of B is 1, then you add those reaction orders, and the overall reaction order would be a 3. And then obviously this order of the reaction is determined experimentally, and you'll be given data on the AP exam. So go to the next slide. Okay. So we want to determine the rate by inspection, which is really quick, and you're going to need to do these for the FRQs. So if we're given rate equals K times the concentration of A to the power of M, concentration of B to the power of N, and concentration of C to the power of P. So for example, if M equals 1, the reaction is first order in A. So you can see the rate equals K times the concentration of A to the power of 1. If A doubles, then the reaction goes up by a factor of 2. So that's when the reaction is in first order. If the reaction is in second order, doubling A increases the reaction by 4. So it's like 2 to the power of 2, which equals 4. And it's exponential. So if you looked at a graph of concentration over time for a second order reaction, it will show an exponential graph. And then if the reaction order is 0, So for example, if the exponent for A is 0, if the rate doubles, the rate stays the same because it does not depend on the concentration. And just to answer real quick, the coefficient of the compound in the reaction, it's not always the exponent. So that's why you need to see it in data. Okay, so here is an example. So for the questions, derive the rate law and K for CH3CHO gas 2 CH4 gas plus CO. So from experimental data for the rate of disappearance of CH3CHO. So you're given this data, and on an FRQ, you'll be given that data. You will never have to like come up the data on your own. So the reaction rate goes, sorry, not the reaction rate. The rate goes up by 4 when the initial concentration doubles. Therefore, the reaction is second order. So for example, if you look at the first and second experiment, when you're looking at the concentration of CH3CHO, for the first reaction, it's 0.10, while this molarity for the second one is 0.2. But then if you look at the rate of disappearance, it goes from 0.02 to 0.08, which means it goes up by 4, which means it's a second order reaction. So then we can say that the rate of reaction equals K times the concentration of CH3CHO to the power of 2, because 2 is signifying that it's a second order reaction. So now we want to determine the value of K using experiment 3, and we're doing this just to make it like consistent, because like whenever you're looking at experiments, you want to make sure it's consistent with all of your data and not just one part of your data. So we're using experiment 3. So we put the K equals, we put the rate of reaction equals K times the concentration squared. So then we can rearrange this. So K equals 2.0. So if you put it into your calculator and do out the math, that's how you would solve for K. And then using this K, you can calculate the rate at other values of the concentration at the same temperature. And make sure it's the same temperature because, like I said before, K changes with temperature. Okay, so just a note, these equations are in the equation sheet, and then these are the integrated rate laws. So these express the reaction concentration as a function of time. So you'll see in each of these reaction orders, you'll see time, the rate constant, and the initial concentration, and the concentration at a particular time. And the form of the equation depends on the order of the rate law. So 0 order, first order, and second order. There may be orders past that, but you'll never be tested on it for the AP exam. You'll only be tested on 0, first, and second order. So for the integrated rate law, we want to look at graphs because you're definitely going to be tested on graphs. And sometimes in the FRQs, you'll be like, oh, the graph of this is a straight line. And then from there, you can determine if it's what kind of rate of reaction it is. So I'm taking this equation of N2O5 going into 4NO2 plus O2. And then from there, you can tell that the rate of reaction is the rate constant times the concentration of N2O5. So if you look at the graph of the concentration over time, it does not fit in a straight line, and the red dots are determined experimentally. But if you look at the plot of the natural log of the concentration of N2O5 versus time, it's a straight line because it's a first order reaction. And if we could just go back to the previous slide. So if you look at for example, like first order reaction, the natural log of the concentration over time, that will create a straight line if it's a first order reaction. And then if you have a graph of the inverse of the concentration over time, then it will be a second order reaction if that's a straight line. So if we can continue, then just skip this slide. Okay, so next is half-life. So there is an equation that I'll show on the next slide, but I just wanted to go over what half-life is real quick. half-life is the time it takes for half of the sample to disappear. So for example, we have decomposition of H2O2. So at the very beginning, it has a concentration of 0.02. And then after the time of 654 minutes, then it goes to half of it. And then after another 654 minutes, it goes to half of that, so that it becomes 1/4. So that's just like an overview of what half-life is. And then for the next slide, we're going to go over a little practice problem on how you might be able to solve for half-life. So for a half-life example, sugar is fermented in a first order process. So the rate of disappearance of sugar is the K times the concentration of sugar. And I'm giving you the rate constant for sugar in this particular temperature, 3.3 times 10 to the minus 4 seconds to the -1. So the question is, what is the half-life of this reaction? So when T equals half of T, so the half-life, then the fraction remaining is blank. But since it's a first order process, we can use the, what do you call it? The equation of natural log multiplied by 1/2 equals -K times T 1/2. And just remember that this equation is on the formula sheet and the equation below it is on the formula sheet. So -0.693 equals -K times T to the 1/2. So as a note for this first order process of half-life, it does not depend on the initial concentration of A. So whenever you have a half-life problem, you can obviously just plug it into this equation if it is a first order process. And I believe like 99% of the time, if you're given a half-life example, it's going to be in the first order. So in order to calculate half-life, you want to rearrange this equation. So it's T 1/2 equals 0.693 divided by K. So for sugar, T 1/2 equals 0.693 over K. And then if we use the K that was given within the problem, it equals 2,100 seconds, which is also 35 minutes. Okay, so for reaction mechanisms, I know this might seem a little bit intimidating, but if you see like the little image above, you can it's called different things depending on how many reactants there are. So there's unimolecular, which is, it's like decomposing. So like, for example, of that H2O2 example, where the rate law will only be dependent on one reactant. And then bimolecular and intermolecular. So that's when you have multiple products, reactants reacting to form products. And then in the rate law, it will show that like there's different reactants. So for example, if you have bimolecular and it's like two of the same reactant reacting, then it would be rate equals K times the concentration squared. But you could also have a bimolecular where it's two different reactants reacting, where rate equals K times the concentration of A and the concentration of B. So molecularity tells us how many molecules are involved in the process. Rate law for an elementary step is written directly from that step. So all of the all of the molecules involved in the elementary step are defined in the rate law. So, and then the sum of the elementary steps in a mechanism must give the overall balanced equation for the reaction. So we'll learn more about this, I believe, on the next slide. Okay, so again, what I said before, most reactions involve a sequence of elementary steps. So for this equation that I have right here, the proposed mechanism is down below where there's a slow step and then there's two fast steps. So things to keep in mind is one, that rate law comes from the experiment. It doesn't necessarily have to come from like a specific of like the whole balanced equation. So, and then order and stoichiometric coefficients are not necessarily the same. So with the question that I had answered earlier, just make sure you don't assume that the coefficient is the same as the order, even though it might be. It's not always always the case. And then number 3, rate law reflects all chemistry down to and including the slowest step in the multi-step reactions. So the rate of the reaction is controlled by the slow step, aka the rate determining step, RDS, and rate can be no faster than the RDS. So the rate of the slow step will determine what the actual rate is. So yeah, and then we can move on. And then I'll be answering questions at the end. I just want to make sure we get through all of this. So for the reaction mechanisms of the same one we had on the previous slide, elementary step 1 is bimolecular because it involves the iodine ion and H2O2. Therefore, this predicts the rate law should be rate equals I minus the ion times the concentration of H2O2 as observed because it's in the slow step. And the species HOI and OH minus are reaction intermediates. And an intermediate is an unstable molecule of low unknown concentration that cannot appear in the rate law. So it might appear in the fast steps, but they won't be in the overall rate law. I hope we're doing okay. Put a thumbs up in the chat if we're doing okay. So now I want to talk about fast initial steps. Oh, it's just to see one question. How can you tell from a table of steps which one's the slow one? It will usually say. So 2NO gas plus Br2 gas equals 2NOBr. So the rate equals K times the concentration of NO squared times the concentration of Br2. And this is by experiment, like this is given to you. And due to the rarity of trimolecular processes, this rate law suggests a 2-step mechanism, which is given to you. And we know this is a trimolecular or termolecular process because there is 2 of NO and then 1 of Br2. And then step 1 is an equilibrium because it includes both the forward and the reverse reaction. So as you can see, it has that double-headed arrow. And then the rate law for the slow step would be rate equals K2 times the concentration of NOBr2 times NO. But how do we find NOBr2? Because it's not the same as the rate law that we have by experiment. So just returning back to the step 1 and step 2 that we have at the top of the screen that was also on the previous slide. NOBr2 can react in 2 ways. So it can either react with NO to form NOBr, which is in the slow step. So it can, as you can see, it goes to 2 NOBr, or it can decompose to form NO and Br2 in the fast equilibrium. And since the reactants and the products of the first step are in equilibrium with one another, the rate of the forward equals the rate of reverse. And that's just the definition of equilibrium. The forward reaction and the reverse reaction are going to be the same. And you're going to learn a little bit more about it in night 2. So due to this, K1 NO concentration of NO times concentration of Br2 equals the inverse of K of NO Br2, so the concentration of that. And solving for this, it is concentration of NO Br2 gives us K1 over K minus 1 times the concentration of NO times the concentration of Br2, which equals the concentration of NOBr2. So basically, it's just putting in equations within equations. So when we are doing that, just remember, like, if you can see for like the due to this equation, we're just basically moving the K minus 1. And the reason why we have the K minus 1 is because we are that is for the reverse reaction of the equilibrium step. So next slide. Okay, so we again have the steps. So let's now substitute this expression for the concentration of NOBr2 in the rate law for the RDS. So I replaced K1 over K, the inverse of K1, to K2 because again, it's a rate constant and it's kind of like changing within the definition. So when we're doing that, we're replacing, so rate equals K2 times what we replaced for NOBR2, which we found on the previous slide. And if you need to look at the previous slide, you can look at it with the resources that are listed. So rate equals K2 times K1 over K minus 1, concentration of NO times the concentration of Br2 times the overall concentration of NO. And then when we simplify that more, we get rate equals K, because we're replacing K by like combining all of them. So K times concentration of NO squared times Br2. And if you remember, that's the exact rate law that was determined experimentally. So I know this is really complicated, but we can go over this if we have time later. Okay, so mechanisms and activation energy. I know we're almost done. So I use this example of cis to trans to butene, which basically you have to twist the double carbon bond. You don't need to know this example, by the way. I'm just saying it just because I find it easier to see it through an example. And this transition state of like it being mid switch is called like the activated complex. So you have to overcome that energy before getting into like the second state. So going from cis to trans butene, you need to overcome the activated complex, which is also known as the transition state. And you can see the energy through the graph. So first you have to overcome 262 kilojoules, and then it will be negative 266 kilojoules, and then you'll have a excess of 4 kilojoules per mole. So basically, this is more of a transition going to thermochem, but this is like how thermochem and kinetics are both connected. But tomorrow during night 2, there will be more of an explanation on this with thermochem. And I think we're on the last slide. Okay, not quite. So for reaction mechanisms, basically explaining what was on the back one, reaction passes through a transition state where there is an activated complex that has sufficient energy to become a product. Activation energy, also known as EA, equals energy required to form an activated complex. And in this example of cis to trans to butene, EA equals 262 kilojoules per mole, which is what the energy that we had to overcome. And then just to note, transbutene is more stable than cisbutene by about 4 kilojoules per mole. And that means that the reaction is exothermic. And again, this is a connection between thermo and kinetics. And when you make this switch, you'll have a release of 4 kilojoules per mole. And again, we're going to go more over this in thermochem. And then I think we're on the last one of catalysis. So catalysts speed up reactions by altering the mechanism to lower the activation energy barrier. So increasing the number of effective collisions and or provide the reaction path with lower activation energy is what makes a catalyst a catalyst. So catalysts may appear in one step, but will appear again as if they hadn't been touched. So it might be consumed in the first step, but then it will reappear by the last step. Because catalysts, while they're used in the reaction, they're not used within like the molecules by the end of the reaction. So like they might be, if anyone had taken bio, they might be like going onto an active site, but then coming right off of it towards the end, and they're not used up. So like, for example, like enzymes are a catalyst. So catalyst binds to the reactants or form covalent bonds with reactants in acid-base catalysis, and then that will be expanded upon in acids and bases, which is in Unit 8. So now I believe we're going into the quiz, and then we'll answer questions if we have time at the very end. I guess while we are going over that, oh my gosh, there's a lot of messages. While we're going over that, So there is the QR code, and then there's a link. If anyone has any questions, feel free to drop it in the chat, and then I can answer this while people are joining in. It's real quiet on the stage by myself, guys.
Hey, I'm here. Hi.
Okay. So, which starts lower on the graph, endothermic, because you're like in the sister transbutene, for example, like you started with a higher energy, and then you're going to a lower one. But then it's the reverse with endo, so you're going from a lower one to a higher one. I hope my explanation was good, guys. I know kinetics is like really hard for some people, so yeah.
And don't forget, night 5 is going to be a lot off of what you guys are needing a little bit more review on and questions that you guys have. So we'll be happy to talk more about kinetics if you need it. Yeah.
Yeah, so K2, like rate constant changes when you're like doing the math for it. But in the end, you'll like get the what the rate constant needs to be. So for example, like you'll have like, for example, like K1 over the inverse of K was can be also known as like K, but I set it as K2 just because it's a little bit less confusing that way. Jahangir, do you want to join us on stage? Come with the rest of the night.
Come join us.
Sure, yeah. Sounds good.
I think the crowd missed you guys.
I think we're stagnating on the people who've joined. I think we should maybe start, and then
Yeah,
if more
let's
people want to
start.
join.
I know kinetics makes like a lot of like no sense. Oh, so like I wouldn't necessarily call it K squared, like because it's just like reforming another K.
What's up, guys?
Hello.
And I'm glad to be back. And chat went crazy.
Hey, are you guys having trouble answering the question? It's coming up as 0 out of 194 or 6 participants. I want to make sure that y'all are answering it. It might just be quiz on wrong. Hey, can we restart the quiz, y'all?
Yeah, let's just
Yeah, let
boost
me
it.
do that. Do we want to start again?
Yeah,
Here.
If it doesn't end up working, we can just have everyone like type their answer in the chat, and then we could just do it like that way.
Okay.
So let us know if this works, and if it doesn't work, just let us know.
Got it now. We're good.
Okay.
I think, at least. People are saying it works.
Okay, yeah, I see people answering.
Okay. Oh, yeah, perfect.
I hope you guys are feeling a little bit better about the first 5 units. I know the hard ones are 6 through 9, but
Yeah.
we're getting there, guys. We just need a good basis.
If any of y'all need the link, it's directly under where it says AP Chem Units 3 through 5. And then also, if you're on a mobile device, you can use the QR code there. However, I personally had some trouble with it. So if you want to use the link, feel free to type it out right under there.
Dang, we're a little over 2 hours into our session.
Yep.
Time has been flying.
Yeah, it is. Well, time flies by when you're having fun.
Right? What's more fun than AP Chem?
Guys. Yes, the recording should be posted as soon as this is over.
Looks like we have most.
Make sure you get some rest
Mm-hmm.
while you're studying.
Especially the week before the exam. Like, this is a very important thing. very important time to make sure you're resting well.
Okay.
Oh,
if you
Holly, you
can-
don't want to stay up till 12 and 1 a.m. Please don't do that. Sleep is important.
Okay, let's reveal the answer.
Yeah.
Okay, nice, 70%.
Okay, yeah, awesome. So the only thing I'll say here, I noticed a lot of y'all put significant. It only becomes significant if the pressure is very, very high, where they're more likely to have collisions with each other.
Okay, which of the following best explains why molecular compounds with polar covalent bonds are generally more soluble in polar solvents than in nonpolar solvents?
This is a fun question.
Yeah, so if you want to hold on to like doing KMT review, we will we're like listening to what you guys need all on like the 5th night, and that's like the really like pour your questions out and then we'll go.
Yep.
Where are we at in terms of answers from participants? Oh, okay, cool, awesome. I understand y'all not having the best sleep schedules as a former AP Chem student. It's really important at this point, though, guys. Like, I know y'all probably don't want to, and obviously, if you're struggling to sleep, that's a very different situation. But if you're willfully staying up till 4 a.m. and waking up at 6 a.m., y'all need to stop, please.
Yeah.
That can cause brain damage. I
Yeah,
think.
the mind actually works better when you sleep. You form better connections when you sleep. Sleep is not for the weak. Please don't say that.
Yeah, I don't know about you guys, but I've been going to bed at 10 or like 11 every single night.
I can't talk a ton. I go to bed at like midnight and I wake up at 6, but I'm still getting better vibes than some of the other people in the chat.
See, I'm an old man and I just sleep at 9.
I think we're stagnating on participants answered.
Yeah, I'll just reveal the answer.
Okay. Awesome. So it looks like we're having some struggle between. Okay. So basically the reason that it's not going to be C in this particular situation is because this is basically asking about polar like meets like. So polar solutes dissolving in polar solvents. And in this situation, it's specifically asking like why molecular compounds that are polar dissolve better in polar solvents. So in this case, you would want to talk about those dipole-dipole interactions and how the polarity, dipole-dipole. No, dipole-dipole exists between specifically polar only. Yeah, exactly. So again, this is a situation of likes meets like, and you would want to focus in this situation on why the dipole interactions are what's allowing the solute to dissolve in the solvent.
Next question. What is the danger of heating a rigid container of helium gas?
This is a little bit more of an applied question. Y'all are going to have to think about your gases especially.
But don't try it in real life.
Yeah, please. No, we don't need any hands-on efforts here. Please no demonstrations. Please no demonstrations. That's not exactly ideal. Also, Juan, hydrogen itself, it needs to be in a hydrogen bond for it to be something that's polar, not necessarily just hydrogen. So water itself is actually an example, or water bonding to another water molecule or something similar is an example of a hydrogen bond.
We're almost there to 200. All right, we beat 200.
I think we could just reveal the
Yeah,
answer.
I would
let's
just
do that.
reveal. Okay,
Okay,
perfect. Awesome.
We did great on that part. I guess you guys know why heating a rigid, we shouldn't heat a rigid container of helium gas, because the pressure of the container will increase, and with that increase of pressure, it's just too much for the hopefully it's a glass or some rigid container. It's gonna be too much pressure, and it's just gonna burst. So you guys got that on point.
I want to
let's
make a
move on to the
real
next
point
question.
real quick.
Hmm?
That wasn't regarding the stability of the gas itself. This is more related to your Pivnert, so your pressure in relation to temperature.
Everyone's talking about Walter White now. It was about time.
Yeah, it was gonna happen. It was gonna happen.
Sorry, I had to
Yeah.
bring it up.
Jesse,
That's such a good
Jesse,
show.
we have to cook. We have to
That's
cook
the only
methane,
reason
Jesse.
why I took chemistry.
Wait, really?
No.
Oh, okay. I was about to
Imagine.
say, wait a minute.
No, I just took chemistry because I wanted to be the danger.
Bro is the one who knocks.
There's a dealer in your AP class, and you call him Walter White. That's crazy.
We'll keep it PG.
We're not condoning illegal activity right now.
Chat GPT for private tutoring is crazy.
Dude, Chad,
Anyways, let's reveal the answer.
please.
Yeah. Okay,
All
awesome.
right, let's go, guys.
That's a pretty split. Again, like I said, just keeping in mind, I personally at least find it a lot easier to just flip the reaction around and then figure out which would be the acid in that case, and then just say conjugate.
If you guys definitely don't know this, we're gonna go over this tomorrow as well. So
Mhm.
that's what acid bases are. So okay, what is the difference between acid-base reactions and oxidation reduction reactions? Unbreakable bad network covalent solid.
Man, ChatGPT and the whole AI stuff is just crazy.
Did you guys see the new Snapchat AI?
Yeah, no, I don't like it.
You can take it out though.
Oh my gosh, there's a misspelling of one of the answers, and now the chat's going crazy. It's protons, guys. It's just protons. The P is next to the O. Perptons.
Yeah,
New-
so on the occasion that you don't pass the exam, we're helping you pass, by the way, because I believe in every single one of you guys. You can always just not send it to your college.
Yeah, and they won't side eye you.
Yeah, they won't.
And
send
it never hurts you. Even if you send a 2, they're not gonna say, "Oh, this person, you got a 2. You're not gonna be admitted to the college." It's never gonna hurt you. All right, I think that should. I'll just reveal the answer. We
Okay.
were kind of on a time
So
constraint.
Okay.
continue, and then I'll answer a question after.
Okay, awesome. Yeah, so basically the reason that A is going to be incorrect in this situation, you can't really transfer pH in this case, or in the meaning that like pH is more a indicator of what is in your solution. You can't really transfer an indicator per se. And then oxidation reduction, understandably why it sounds like transfers charge, but again, it's a situation of it's more a demonstration or a word to simplify the actual thing that's going on, which is why C is the better option in this case.
Yeah, and so while we're answering this question, so you can technically retake an exam, like you'll still have it, but like the next year, if you're like, okay, well, I want to take it again, then you could totally do that.
I think there's some confusion. I believe that Ruth was talking about the $15 for the cram pass, not for the $100 for the AP test. However,
Yeah.
if you got scammed $100 by a secondhand source for your cram pass. I don't even know what to say there.
Guys, your test score doesn't define you.
Yeah.
And especially for like this like cram session, it's like what you put into it as well. Like you gotta put some work into it as well. So
Exactly.
make sure you guys practice questions. That's like the best way to do well, because when you're like actually sitting down doing an AP exam, like a practice AP exam, it's gonna be exactly like that on the test. And they're like the most I guess like predictor of like how you're actually gonna score.
All right, I'm gonna reveal the answer.
Okay.
Okay, so this one was split. I'm curious what A picked. Okay. So I think there's no question error. I just want to check with you two, right? I can check real quick if we want, or someone else can check to make sure. But in this case, zinc is the thing that is being reduced because excuse me. Zinc is the reducing agent in this case because it gets flipped. So in this case, zinc ends up losing 2 electrons. It is being oxidized. However, reducing agents are weird because it's the opposite. So the reducing agent is the thing being oxidized, oxidized, and the oxidizing agent is the thing being reduced. And I'm glad I put this question in because I was a little worried about that. But yeah. You put zinc, but it said you were wrong. I'm not sure why.
Did you accidentally put like zinc
plus 2?
Yeah, plus 2.
All right, next question. Combustion reactions only involve which of the following? Looks like it's a concept question, so it's either you know it or you don't.
Yeah, it's the reducing agent, not the one being reduced. Chemical reaction of our own.
All right, let's reveal the answer, and it is organic molecules.
Nice job, guys. Remember that like organic molecules are with hydrocarbons, I believe, which are organic molecules. Hydrocarbons include like I think it's like carbon, hydrogen, and then I'm not sure if it's oxygen, but yeah.
All right, guys. We're gonna have to cut the quiz a little bit short so we can have a Q&A talk. So I'm gonna end screen sharing. And
Awesome.
let's look at the questions that we have. We got a lot of questions. Most of them have been answered by everyone else who's in the chat. And which one should we choose, guys?
Well, there's a ranking system. So I think going from the top of this list, we can throw each question on stage based on the number. So that means you guys, if there's a question that you see in the Q&A tab and you want to rank it up, feel free to do so.
Yeah.
Okay, when it asks for the moles of oxygen in a substance, do we solve for O or O2 because oxygen is diatomic?
You definitely want to solve for just oxygen itself because O2 is usually going to be oxygen gas. And when you do this, for example, if it's carbon dioxide and you're finding the specific moles of oxygen, you're going to have a mole ratio of 2 oxygen over 1 carbon dioxide.
Yeah.
So you always want to remember that you're solving for oxygen if it asks so. And O2 is usually going to be gas. So that's the answer for that question. And let's look at this one.
Electron affinity. Awesome. So electron affinity is basically the measure of attraction between the incoming electron and the nucleus. So basically the positive part of one atom and the negative part of the electron cloud of another. So basically it's saying like, based on how close the nucleus is to another's electron cloud, how how much they want to come together and form a bond with one another. Would you guys say that that's a good representation?
Yeah.
Okay, cool.
By the way, like in the chat, let's like stay on task.
Mhm.
Don't talk about how much you paid for your AP exams. Put in the questions in the chat if you have anything.
Next one.
Okay. So this is a pretty interesting one in my opinion. So the quizzes that we do are definitely to primarily go over your basic concepts. However, we're going to be talking a lot about the skills for the multiple choice that you need and some examples for your AP multiple choice during night 3. However, we also know that chances are you're probably doing a lot of multiple choice problems on your own. So we really want to make sure your foundational concepts and then your understanding on how to approach these problems is really solid. If we have more time on night 3, or if we want it on night 5, we can definitely go over some more multiple choice problems. However, for this, and especially when looking at the like the quizzes, those are going to definitely be going over your concepts rather than like specific pulled from page multiple choice.
Yeah.
Elias, I think people are asking if you could like repeat your explanation for electron affinity.
Electron affinity.
Just like what it is.
Okay. So yes, electron affinity is going to be the attraction between the electron cloud specifically, and then your nucleus, which specifically your proton in the nucleus. And this is based on how close the electron cloud is. So if you have more shields, your nucleus is going to be farther away from your electron cloud. And the charge of what you're working with, which is why fluorine is going to be your most oh gosh, the words evading me. Electronegative, is that the word I'm looking for?
I'm guessing so, yeah.
Yeah.
All right.
And
next question, and this is one that I've debated over when I was learning Unit 3. And is the distance or charge from the Coulomb's law equation more important? And for this question, you're never going to be tested on depending on if the charge is more important or the distance. Because in theory, distance is because distance is squared and it's overcharged. But if you look at the periodic table that I have right here, yeah, I live with this thing because it's just AP Chem. So if you have something like let's say you have lithium and you have magnesium, right? So lithium is going to have a smaller atomic radius, so it's going to have the least distance, but magnesium is going to have a higher charge. So the question comes, which one is going to be more attracted to? And the AP questions are never going to ask you that because they know it is a difficult question because it's very debatable. It could be lithium because lithium has less distance to create more traction, but then magnesium also has that 2+ charge. So don't worry about that part. It's going to be pretty obvious. All right. Next one.
either one of y'all want to get it, or I can get it if we want.
Oh yeah, I get it. So calculating your bond angle, you just remember your VSEPR graph, because that's going to show you all your bond angles. For example, linear shape would be 180 degrees. I gotta memorize it too, guys. Tetrahedral, maybe it's like 109.5 or something, but you gotta memorize it. And the best way that I memorized it when it was like I think it was unit 2 exam, is that I found the VSEPR formula on Google, and then I stopped looking at it and I wrote all of it on a piece of notebook paper, and I kept on doing that because that's active recall. That's one of the greatest study methods that you could have. Just looking at the textbook or the graph or whatever you need to, looking at the diagram, then putting that away, putting that aside, and writing as much as you can from memory. So that's how you find your bond angles. I don't know if you'll be calculated. I don't know if you have to calculate specific bond angles.
There's no specific like formula to use, unfortunately. You just kind of have to know based on the Lewis diagram.
And you won't get like that chart on the test.
Yeah.
Yeah.
So you gotta memorize it. All right, next question. When an electron is ejected, does it have higher velocity if it is released from a subshell closer to the nucleus or farther away from the nucleus? Guys, what do we even have to know something like this? Because I don't know. I've never.
I'm trying to think of the context of this.
It's for the electrons spectroscopy or something like that. Well, I can definitely say that it's harder to take an electron that's closer to the nucleus, and it's also harder to take an electron that forms a complete shell. Like it will take more energy to take that away from an atom rather than like something that's farther away or like an incomplete shell.
All right,
I hope
next
that
one.
helps.
Oh yes, I think you're the expert on this one.
Oh, me? Okay. How does the test work? It works strangely. What are you doing? Anyways, so yes and no. So every year there is not a specific set like percent given to you. Like, here's your test. By the way, you have to get a 52 to pass. However, there is a basic like predicted raw score you would have to get every year. I want to say it's in like the 72-ish range on average to get a 5, and then 63% on average for a 4. And then that's taking into account the weight of the FRQ versus the multiple choice section. And it's not graded on a curve per se in the sense of like the person who gets the highest sets the bar, but it is definitely a lot more forgiving than like a test in class would be, for example.
Yeah, so so all of like the College Board questions, whether it's MCQ and FRQs, are like rated in like difficulty. So there's like easy questions, like average, and there's hard questions. So if the exam is like considered a harder exam, then it will have like a greater curve, for example. But exam, unfortunately, there's not going to be as much of a curve.
All right. Oh yes, another question for you.
Uh-oh. Okay, so I'm trying to think of the easiest way to explain this. Essentially, it's because the amount of electrons in the electron shell sphere increases the larger the molecule gets. And that means that it's able to create a stronger temporary dipole because the attraction of more electrons is able to move towards one side of the molecule or the atom. Rather than if there was less electrons, there's only so much negativity that you can get on like one side or one area of the molecule between two molecules that have LDF, London dispersion forces, which is all of them.
Yeah.
One question I just saw in the chat is like, how do you prevent overthinking the questions? So just one thing real quick, we're going to also have more advice for the test on nights 3 and 4. But just to answer this question real quick, you have to also remember that you have like, I don't know how much it is this year. It's like 1 minute per like MCQ or something. I want to say it's like 1.5, something like that. And so you can't spend that long on an MCQ. If you really are just like, I really don't know this question, skip it, move on, star it, come back to it. And yeah, and then honestly, like one tip that I personally have is like to read the question, think of the answer in your head, and then see which one matches your answer and which it like matches of the listed given ones.
All right, Elias, another question for you.
Oh, that's so many questions. Okay, examples of ion dipole forces. I'm gonna have to think for a second because it's been a year. Oh gosh.
Big one would be table salt, sodium and chlorine.
Yeah.
That would be a big one.
Is that? I guess so.
Yeah.
Or chloride, my bad.
I'm checking the notes real quick. I'm gonna be honest, because it's totally fine to do that at this stage. You know, we're still studying. And if you need to look back on something, it's not bad to do that. So you're right. Now that I think about it, it is NaCl is a good example. feel like that's the really big one. I want to say NaOH is another example, and I think that's a little
think
bit
it
clearer of
is,
an example. That I using the model that I gave. I think that's a bigger, like, clearer one with the model that I built.
Because the reason why I'd say it's an ion dipole is that when it's put into water, sodium and chlorine separate. So
Oh,
then
I
the water binds to sodium, specifically, or oxygen binds to sodium. So that's where the ion dipole forces come together.
I think it's like
You're
relatively
right.
like any soluble salt, yeah. Like the alkaline salts, the
I think NaCl completely dissolves, I want to say.
yeah, I believe so.
I think so, yeah.
Yeah.
All right, another LDF question.
Oh, okay, that's me. I'm getting so many LDF questions. Okay, okay. I think in this situation, you have to be given the strength of your forces in a graph, or like a table, not a graph per se, but a table. Because I don't think you're expected. I'm trying to think because I don't want to straight up lie to you. I think if it's an example where it's like a huge molecule versus like water, I don't know. I'm trying to think of a good example.
I think like
Oh.
most of the time hydrogen bonding is like always like this.
Yeah.
And I think if it's not, you're usually going to be given a table.
Yeah,
that,
it's like the strongest besides like ion dipole. I think ion dipole's on top, and then it's hydrogen, and then it's
Mhm.
like dipole.
Yeah. But that's
And
interesting. What FRQ was that shown on?
I think I remember seeing something similar, and I can't remember if I was given a table for that one. But I want to say anything that I've seen where it was like there is a subversion of expectation, knowing the general rules. It
I
will
think
tell you that.
I think I've seen like an FRQ where you have to like rank them on like
Mhm.
which is the strongest to like least strongest.
Okay. This we're definitely going to acknowledge this, and we'll talk about that in Unit 5 because we'll definitely go over kinetic molecular theory. So I just want to acknowledge that one. And look at this one. How can you tell if something is networked without a diagram?
Y'all are throwing all the.
I'm guessing they're referring to covalent network.
Yeah. So in that situation, you're just gonna want to know the major examples. You're usually gonna be given like something that's very crystallic, diamonds, quartz. I can even, if y'all won't side-eye me for it, I can look up a list of the most important network covalent bonds for y'all to know. However, it's not very frequent that you're gonna see that unless they're talking about diamond, or I've seen quartz a few times. Those two you just want to know, and then you can also think about your properties of your solids. And know that like crystals are always going to be very rough and hard, and keeping that, and then have very defined structures to them, and keeping that in mind, you can use that to guide your mentality of what it's asking about.
Also, I'm not sure if we're going to talk about it, but also remember like how due to hydrogen bonding, water has a crystalline structure when it is a solid, and like the different components and like factors of water that makes it special. I know that's more of like an AP Bio question, but I have seen it on AP Chem.
Yeah. And you could also just remember that covalent bonds only occur with nonmetals. Is that correct? Nonmetals as covalent bonds?
I want to say that sounds correct, I believe.
I think so. So
I have not heard of an example of a covalent bond that's also a metallic bond.
I don't think there is. So
okay. Now let's look at this one. What is the difference between oxidation number and charge? That is a good one. And oxidation numbers can vary, while charges are just going to be the same, just going to stay the same. So, for example, oxygen, our charge is obviously going to be -2. And for our oxidation rules, it's also going to be -2. But if we're looking at a, let's say, element, I'm trying to think of a molecule, but sometimes, like for example, nitrogen, if nitrogen is with a maybe like some molecule with oxygen, nitrogen doesn't always have to be I believe it's -3. So there's different elements don't have to be the same charge for oxidation numbers, and it's always, you want to know that hydrogen will always be its charge for the oxidation number. Hydrogen will usually always will be +1. Oxygen will be -2, and if it's by itself, like for example, if it's just calcium or it's just calcium ion and nothing else, then it's going to have neutral charge. And if it's Cl2, neutral charge. So that's how they can vary. The oxidation numbers don't always have to be charged, while charge will always be the same. You'll always know what the charge is, but you won't always know what the oxidation number is. It depends on the question.
Good explanation.
Thank you. We already answered the LDF strength increase as mole size increases. It's interesting.
Okay, is Graham's law of fusion mandatory to learn for the test? Yes, you have to know it. You're never going to be given a 7-part FRQ based on Graham's law of fusion alone. The most you're probably going to see is either one like sub question of an FRQ or like a couple of multiple choice or both, you know. So you do have to know it, and you have to understand the reasoning behind it, for lack of a better word. But it's not like you have to have a PhD in Graham's law to be able to do well.
I see like kind of a question in the chat. It says like, no, I mean, because equilibrium basically rate of appearance equals rate of disappearance, except when Q not equal to K. So I might have missed a question before that, but Q equals the concentration of products over concentration of reactants. And during equilibrium, Q equals K. So Hunter will be going over that in Unit 7 tomorrow, because that's where when equilibrium is. So if you want a more precise answer, then stick around for that tomorrow.
Yep. This question might be formatted differently because I'm not really understanding it.
Oh, my bad. But yes, continue. How do you?
Ooh.
I'm not really sure what that means.
But Arnika had a good explanation, and I'll just say it out loud. Formal charge equals valence electrons minus number of lone pair electrons plus 1/2 the number of bonding electrons is the equation you want to use. The non-bonding electrons are counted as part of the lone pair electrons. So if you guys had any questions on that, just look at the comment that Arnika posted, and that should answer the question. Because I mean, I gotta be honest, I really don't know. I really don't know how to answer that question.
Yeah.
If anyone wants to like reword it, maybe.
Oh, I like this next question. Here, is it going to pop up? There we go. This is a fun question. You two start, because I'm probably going to have a slightly different answer.
Okay, Anuva, you got it?
Oh, organic chemistry is great. Organic chemistry tutor is great. I love Khan Academy, which is like kind of YouTube. What else do I watch on YouTube? I usually use those two. Not necessarily on YouTube. On the AP Daily videos are really good, especially the review sessions from past years and even this year. But yeah.
Yeah, and I was thinking of, there's a teacher named Gordon Watson, and you could just search out Gordon Watson AP Chemistry, and he has a bunch of videos that are very insightful. You're gonna have to ask your teacher for him to release the practice test questions that he has, and there's a bunch of MCQ questions, practices for that. So it's just search up Gordon Watson on Gordon Watson AP Chemistry online, and I'd also say, yeah, like Anuva said, organic chemistry tutor, Khan Academy is great. They have great questions, great practice questions. And also ask your teacher for them, ask your teacher to give you access to the MCQ for 2019, the AP Chemistry 2019, 2018, whichever one, because those are really helpful, and also the FRQs. And
Okay. Sorry.
no, you got it, Ellie. So I was gonna...
I'm about to give the most non-answer answer y'all will ever hear. Don't go looking for specific channels necessarily. Just look up concept you struggle with, multiple choice question. You know what's going to come up? Random chemistries from all over, or chemistry teachers from all over the world making videos on how to show it to their own students who uploaded it to YouTube for their own convenience. But bada bing, bada boom, you have access to it now. These videos might not consistently be the best. There will always be so many more to look through, and you're going to eventually find either a channel, like a very obscure channel that works very well for you because it's some random chemistry teacher in, I don't know, like Utah, or like just search up the concept rather than a specific channel, because if you're going for a specific channel, you can't guarantee it. Where the biggest non-guarantee is the first video you will find won't be right for you if you just look up the concept first. Now, I know that's not what you were asking for, but I noticed additional multiple choice practice or more detailed concepts. And my brain was like, I can't give a specific channel. I can say, go find one that works for you, you know?
Yeah. All right, next one. How do we know if the covalent bond is nonpolar or polar if the numbers are not given? Okay, so this is basically a question of what is polar versus nonpolar. And when you're having to identify if a molecule is polar, you always want to either set up a Lewis structure and see what that would look like, and it would be either asymmetrical and it would have lone pairs, and the lone pairs would make it asymmetrical. So for example, H2O or water, that is polar because you have two lone pairs and those are pushing against the hydrogen, making it asymmetrical. And for a nonpolar molecule, you have methane, and methane is C, and then you have HHHH. So it's symmetrical. There's no lone pairs, and that's what makes it nonpolar. So I think that's a question of how do you know if it's polar or nonpolar, and covalent nonmetals. So that should answer the question. Here's a new one that popped up. For hybridization, even if a bond is double or triple, does that count as one? So I'm guessing you're thinking of what it would look like. So, and paper for this. Okay, so I'm guessing you're thinking of something, and this is just a random element that I'm making up. So maybe you're looking at something like this. You're looking M and X and X. So when you're looking at double bonds or triple bonds, pretend this is just one. This is just one group, and this is one group as well. You have two of those. Two, that's going to be sp hybridization. And if you wanted to write, let's say M, and then we have a triple bond right there, double bond, and a single bond. So you have something like this. You're still going to interpret that triple bond as one. You're going to interpret this as one and the double bond as one. So even though if they're double bonds or triple bonds, you just think of it as one. So that's 1, 2, 3. That's going to be sp hybridization. That's going to be hybridization of sp2. So that should answer your question.
Awesome. So we're actually starting to get to an endpoint, guys. We have about 3 minutes, so we're going to start wrapping it up for the evening. We hope that tonight was really helpful for you guys. We know that AP Chemistry is a lot of very dense information thrown at once, and our big goal is to help you, one, realize that, like, hey, you know more than it sometimes feels like, but also to give you a nice refresher. Is there anything my co-hosts would like to say?
Honestly, take a deep breath. We got you within this process. Just to look forward for the next nights. For tomorrow, we'll be going through units 6 through 9. So that's thermochem, equilibrium, acids and bases, and applications of thermochem. And then, yeah, tomorrow's going to be the hard stuff. Night 3 is we're going over MCQ, and then night 4 is FRQ, and then night 5 is like all up to you guys, where we're going to do the majority of like stuff you want us to do over. So I'm pretty sure we have like surveys for nights 3 and 4 based on like what you guys need. So yeah, so tomorrow we're gonna have different hosts. Well, Jahangir's gonna be there, but me and Elias are gonna be in the chat. But yeah.
Yeah, today was an amazing day. We had our first AP grand finale, so you are 4 more steps ahead. Or Monday is the day, and Anuva and I are with you guys. We're taking it with you guys on Monday. Unfortunately,
I'm here with you in heart.
She has to take Gov, and then she has to take AP Chemistry.
Yeah.
So I have a little bit time to cram, even the cram on cram. But yeah, today was a great day, and we'll see you guys later. We'll see you guys tomorrow. Thank you.
See you guys.